Ever wonder what it'd be like to hop in a time machine, zip through the ages, and pop out at, say, a Roman gladiator match or a party with folks from the year 3000? Time travel's the stuff of science fiction dreams. But here's the kicker. It's not just for novels and movies. It's as real as the stars above, woven into the very rules of the cosmos. Time's not some rigid line, it's a river you can twist, stretch, maybe even loop. Chasing the idea of time travel doesn't just spark the imagination. It pulls us into the universe's deepest riddles, showing us how wild and weird reality can get. Let's rewind to 2009 Cambridge, England. The legendary physicist Stephen Hawking, the guy who tangled with black holes, and the Big Bang decided to throw a bash. But this wasn't your typical wine and cheese deal. Hawking set out a spread of champagne, and snacks rolled out the red carpet and sent invites to time travellers only. Here's the twist. He didn't mail those invites until after the party was over. Genius, right? If anyone showed up, it'd mean they'd crack the code to jump back from the future. So picture Hawking waiting in a quiet room, clock ticking, hoping for a knock. Spoiler alert, nobody came. Zilch. Nada. Does that mean time travel's a bust, or maybe the future knows Hawking throws lame parties? Here's the deal. We're all time travellers in a boring sort of way. Every second you're sliding into the future tick-tock 60 seconds a minute. But when we talk time travel, we mean the good stuff. Leaping years ahead or slipping back to the past. How do you pull that off 100 years ago? Albert Einstein flipped the script on reality. He didn't hand us a shiny time machine, but he gave us something crazier. A new way to see the universe. Forget thinking of space as a giant box and time as a clock on the wall. Einstein said they're one thing. Space. Time of four. Dimensional dance floor where every move matters. Think of it like this. Space. Time's a big, stretchy sheet. The 3 dimensions of space up, down, side to side tangle with the 4th time to make a single stage we're all moving through. Stand still and you're zooming through time at max speed 1 second per second. But start moving through space and it's like you're trading some of that time. Speed for space. Speed. It's not magic, it's physics. Ever notice how a day is just the sun climbing and dipping, or an hour is a clock's hand sweeping time and motion are glued together? Now let's say you're in a car, foot off the gas, just chilling. You're the car, the road, it's all cruising through time second by second. But slam that pedal and something wild happens. The faster you go through space, the slower you move through time. It's like the universe says, hey, you can't have it all. Scientists call this time dilation, and it's not just a theory, this has been tested. Back in 2015, astronaut Scott Kelly blasted off to the International Space Station, zipping around Earth at 17,000 miles an hour for a year. Meanwhile, his identical twin Mark stayed grounded. When Scott touched down, he'd aged just a smidge less than Mark by a tiny fraction of a second. He'd nudged into the future ever so slightly because his speed warped time's flow. That's cool, but what if you wanted to jump way further? Like let Earth age 1,000 years while you barely blink, you'd need to go stupidly fast, close to the speed of light, 186,000 miles a second. To put that in perspective, the fastest humans ever, the Apollo 10 crew, hit 25,000 miles an hour. You'd need to go over 25,000 times faster than that. Good luck. Building a ship to hit those speeds would take more energy than humanity's ever dreamed of. The universe doesn't make time travel easy. But speed's not the only trick up the cosmos sleeve. There's another player. Gravity. Einstein showed us gravity is not just a force, it's a dent in that space. Time sheet. Big objects like planets or stars warp it, slowing time in their grip. Here on Earth, it's subtle. If you live in a skyscraper's penthouse, time ticks a hair faster than in the basement where gravity's stronger. But out in the universe, gravity gets wild. Imagine a black hole, a cosmic monster so dense it swallows light itself. Near one time doesn't just slow, it practically crawls. Picture the heart of our galaxy where a beast lurks. Sagittarius. A supermassive black hole packing the heft of 4 million suns. Its gravity doesn't just bend space. Time, it warps it into knots. Get close and time starts to stumble. An astronaut circling its edge might feel a few hours pass, but back on Earth decades could slip by. To folks watching from afar, the astronaut's signal would slur their face on the screen, freezing like a glitch in reality. Yet for them aboard their ship, every heartbeat feels normal. That's the eerie truth of a black hole. It's a time machine carved by the universe itself, flinging you into tomorrow without a single button to press. Now let's say you're bold enough to nudge closer, right up to the black hole's edge, the event horizon where light itself gets trapped. Things get weirder. Your ship's lights would dim, reddening as gravity saps their energy. To mission control, you'd look like you're stuck suspended in a single moment. But inside time ticks on as always. Push further toward the core, the singularity and the rules of physics just quit. It's a place where space, time phrase a cosmic dead, end where what happens next becomes anybody's guess. Could it be a doorway to another time, another universe? Nobody knows, because anything crossing that line doesn't come back to tell the tale. Here's the catch. Black holes are great for skipping into the future, but they're a once-way ticket. Want to zip back to 2009 and crash Hawking's party that's trickier? To go backward, you need something even wilder than a black hole, something that doesn't just bend space. Time, but punches right through it. Enter the wormhole, a theoretical tunnel that could link 2 points in the cosmic sheet, like a shortcut between pages in a book. Step into one end and you might pop out years earlier, or light not years away. It's the kind of thing that makes physicists' eyes light up and sci-fi writers reach for their keyboards. But wormholes aren't exactly lying around for us to stroll through. They're fragile, finicky things, and keeping one open is a nightmare. Gravity wants to snap them shut, crushing anything inside. To hold a wormhole's throat wide, you'd need something bizarre. Negative energy, a kind of stuff that pushes instead of pulls. Sounds like fantasy, right? Well, the universe has surprised us before. Take dark energy, it's real, driving galaxies apart, but it's not quite weird enough to prop open a wormhole. Still, some scientists wager we might one day find the right kind of exotic matter. If we do, we could build a bridge to the past, maybe even send a note to Hawking saying, hey, spice up the playlist, let's say we crack the wormhole code. You find one anchor, one end in 2025, and sling the other end near a black hole where time slows to a crawl. Wait a bit, and the two ends drift apart in time, one stuck in the present, the other lagging in the past. Hop in the present, side entrance, and you could tumble out years earlier. But there's a limit. You can go back before the wormhole was made. So unless someone built one before 2009, Hawking's party is still out of reach. Bummer. Now let's get real for a second. Even if we could jump back, time travel to the past stirs up some serious head scratchers. Ever heard of the grandfather paradox? Imagine you zip back to 1950 and oops! Stop your grandpa from meeting your grandma. No parents, no you. But if you were never born, how do you go back to mess things up? Your brain's doing cartwheels, right? It's like the universe is saying nice try, but this doesn't add up. Some folks think this paradox proves backward. Time travel is impossible. Physics just won't let you break the rules. But what if the universe has a workaround picture reality as a giant dimensional scrapbook where every moment past, present, future sits side by side already written? This is the block universe, a place where time doesn't flow, but just is. Your birth, your first kiss, Hawking's empty party, they're all pages in the same book existing at once. If you could step outside this scrapbook, you'd see dinosaurs stomping spaceships soaring, and that 2009 bash all frozen together. Time travel in this view is just flipping to a different page. Here's the wild part. In a block universe, you can change the story. The grandfather paradox dissolves because you didn't stop your grandpa, it's not on the page. Nobody showed up at Hawking's party, so nobody ever will. It's locked in. This idea makes time travel to the past feel less like an adventure and more like a guided tour you can visit, but you can rewrite the script. Still, it's a mind bender, and it pushes us to ask, why does time feel like it's moving forward at all? Why do we remember yesterday, but not tomorrow? That question takes us to the universe's opening act. The Big Bang 13.8 billion years ago. Everything space-time energy burst from a single blazing point. It was a moment of perfect order, like a freshly baked cookie before it crumbles. Ever since, the universe has been spreading out, getting messier, more chaotic. Scientists call this entropy the slide from order to disorder. Drop a mug and it shatters. Spill coffee and it spreads. You never see the pieces jump back together or the coffee leap into the cup. There's entropy at work, and its Y-time seems to have a direction forward toward chaos. So why does time feel like a one-way street? Why do we look back at broken mugs and spilled coffee, but never see them leap back to wholeness? This forward march, this arrow of time, is tied to the universe's slow unravelling. Entropy that slide from order to chaos is the culprit. It's why eggs crack and don't uncrack. Why your room gets messy but never tidies itself. And it all traces back to the universe's first heartbeat. The Big Bang 13.8 billion years ago, when everything exploded from a single impossibly tidy speck. Imagine that moment. A pinpoint of energy hotter and denser than anything we can fathom, perfectly ordered like a cosmic snowflake. From that spark space, time unfurled, stretching and scattering. In a cosmic blink, the universe ballooned. Within 380,000 years, atoms started knitting together. A couple 100 million years later, stars sparked to life, clustering into galaxies. But with every step, the universe got messier. Galaxies drift apart, stars burn out, and order gives way to disorder. Fast, forward, trillions of years, and the cosmos might be a cold, dark sprawl with no stars left to shine. That's entropy's long game, and it's why time seems to flow from past to future, never doubling back. This arrow of time isn't just a cosmic quirk, it's a hurdle for time travellers. If you jump back to a less chaotic moment, you'd be swimming against entropy's current, trying to rewind the universe's mess. It's like trying to scramble an egg or rebuild a shattered mug from memory. Some physicists think this might be why backward time travel feels impossible. Entropy's like a cosmic bouncer saying, keep moving forward, pal. But what if there's a loophole? What if the rules bend in a realm where the universe plays by a different playbook? Let's shrink down to the subatomic world where quantum mechanics runs the show. Here the universe gets downright bizarre. Tiny particles, quarks, leptons, bosons, don't act like anything we know. They can slip through walls, pop into existence, or vanish without a trace. Stranger still, the laws governing them don't care about time's direction. In the quantum realm, forward and backward aren't set in stone. It's like a game where the rules let you move any which way, and the arrow of time starts to wobble. In 2019, a team of Russian scientists decided to poke at this idea. Using a quantum computer, they nudged an electron to act like it was moving a fraction of a second backward. Not a big leap, just a flicker, but it was enough to raise eyebrows. They figured out that in theory, this kind of backward hop could happen naturally, maybe once in the 13.8 billion year history of the universe. That's not exactly a reliable bus schedule to Hawking's 2009 party, but it's a crack in the door. If quantum particles can ignore times, how could they carry user at least a message back to the past? Here's where it gets wild. The quantum world isn't just about particles, it's about possibilities. Say you send a particle back in time like an invite to Hawking's bash. In our everyday world, that might seem straightforward, one timeline, one outcome. But quantum mechanics throws in a twist. Every choice, every particle's path could split reality into multiple threads. It's called the many worlds idea. If you sent that invite, it might land in a new universe where the party's packed with time travellers, but our universe, where Hawking waited alone, stays unchanged. You're not rewriting your past. You're just visiting someone else's. This is head. Spinning stuff, I know. Imagine trying to send a note to your younger self with, say, next week's stock market numbers. If the many worlds idea holds, that note might spark a new reality, where you're rolling in cash, but the you in this universe still stuck refreshing your bank app. It's not time travel as we dream it and hopping back to fix mistakes or crash parties. It's more like hopping sideways into a different story, one where things play out differently from the jump. Now let's talk practical for a second. Even if quantum time travel is real, it's not like we're booking tickets to ancient Rome. Your body's made of more particles than there are stars in the sky. Breaking you down to subatomic bits, sending them back and rebuilding you without scrambling your memories, that's a sphere pipe dream for now. But what about sending information? We already use quantum particles every day. Electrons zip through your phone. Photons carry your texts across the globe. If we could encode a message on a particle and flick it backward even a tiny bit, it'd change everything. Imagine whispering to 2009, "Hey Hawking, throw in some better snacks next time." But here's the rub. Even if we pulled it off, quantum mechanics might still trip us up. That many worlds idea means your message could end up in a parallel reality, not your own. And if it did land in your timeline, would it even matter if nobody showed up to Hawking's party? Maybe the universe is wired to keep that moment empty no matter how many invites you send. It's enough to make you wonder if time travel's less about changing the past and more about understanding why it's set the way it is. This brings us back to the big question. Why does time feel so stubborn? Why does it march forward, locking us out of yesterday? The answer might lie in that cosmic scrapbook we mentioned. The block universe where every moment exists at once. If that's true, time's not moving. We're just experiencing it in slices like flipping through a photo album. But the quantum world hints at something else, a place where time's rules soften, where the past and future might blur. Maybe that's where we'll find the key to unlocking time's deepest secrets. But you can't rewrite the script. It's a cosmic rule book, and the pages are set. Still, the block universe doesn't explain why we feel time marching forward, why yesterday's memories are sharp but tomorrow's are blank. That's the puzzle that keeps physicists up at night, and it's tied to the universe's slow drift toward disorder. But what if we could dodge that drift slip through a crack in reality and visit the past? Not just in another universe, but in ours. Let's dive deeper into the quantum world where the rules get fuzzy and time's arrow wobbles like a spinning coin. Those Russian scientists in 2019 showed us a glimpse. An electron nudged backward just a hair in a quantum computer. It's not like they sent it to the Stone Age, but it was enough to hint that time's flow might not be ironclad. In the subatomic realm, particles don't care about before or after. They dance to a different beat, one where the past and future blur. If we could harness that, could we send something back? Maybe not a person, but a signal, a whisper to 2009 saying hawking your party needs more pizzazz. Here's the tricky part. Quantum mechanics doesn't play nice with our dreams of time travel. That many a world's idea, we mentioned it's a game. Changer. Every time a particle makes a choice like zipping left or right, it might split reality into two paths. Send a particle back to Hawking's party, and you could spark a new universe where the room's packed with time, hopping guests. But in our universe, the one we're stuck in the chairs stay empty. It's like mailing an invite and realising it went to a parallel reality's mailbox. Your past stays untouched, and you're left wondering if you even made a dent. This many. World's twist makes backward time travel feel less like a victory lap and more like a cosmic detour. Want to warn your younger self about a bad decision? You might create a new timeline where you dodge the mistake, but the you in this reality still lives with the consequences. It's enough to make you question what time travel's even for. If you're just hopping to someone else's story, are you really travelling, or are you just visiting? Still, the idea's tantalising. If we could send information back even to a parallel world, it'd open doors we couldn't yet imagine, like playing the stock market across universes. But let's dream bigger. What if the universe has another trick? Something beyond wormholes or quantum leaps. Imagine a place where time doesn't just bend but loops back on itself like a cosmic pretzel. Physicists call these closed time, like curves, and they're as wild as they sound. Picture starting your day moving through space and time and somehow ending up right back where you began, not just in the same spot but the same moment. It's like living the same Tuesday over and over but on purpose. These curves could let you stroll into your own past, no wormhole required. Here's where it gets nuts. Closed time. Like curves might exist in the universe's most extreme corners, where massive objects like the hearts of black holes twist space, time into knots. Imagine two super-dense objects, not quite black holes, spinning around each other so fast they drag reality into a loop. Step onto that path and you could circle back to yesterday. But there's a catch, there's always a catch. These loops don't let you change what's already happened. In the block universe, your past is etched in stone. If you didn't show up at Hawking's party, you won't no matter how many loops you take. It's a time machine with handcuffs. This brings us to the big why. Why does time feel so stubborn, locking us into one direction? We've got entropy pushing chaos, the block universe freezing moments, and quantum splits creating new realities. But the universe might hold one last clue buried in its birth. The Big Bang wasn't just a bang, it was the starting gun for time itself. From that perfectly ordered speck, everything's been unwinding, spreading, breaking apart. That's why we see eggs shatter but not reform, why we age but don't untaunt age. Time's arrow is the universe's story, and we're all characters in its pages. So where does this leave us? Time travel's not a button you press or a car you rev to 88 miles an hour. It's real, but it's messy. Speed up, and you can skip into the future like Scott Kelly did for a fraction of a second. Orbit a black hole and you might leap centuries ahead. But going back, that's the holy grail, and it's guarded by paradoxes, entropy, and the universe's own rules. Wormholes might work if we find exotic matter. Quantum particles might carry messages if we navigate the many. Worlds maze. Closed time, like curves, might loop us back if we can find them. But each path comes with a question. What would you do if you got there? If I could slip back? I'd love to wander ancient Rome, feel the roar of the Colosseum. Or maybe I'd peek 13 billion years ago, watch our galaxy spin into being. Heck, I'd settle for showing up at Hawking's party with a better playlist. But time travel's more than a vacation, it's a mirror. Wrestling with it forces us to face the universe's toughest riddles. Why does time exist? Why does it flow one way? Thinking about these questions doesn't just spark wonder. It reshapes how we see reality itself. Here's the truth. Time travel's still more sci-fi than science fact, but it's not a dead end. A century ago, ideas like black holes or quantum mechanics sounded like lunacy. Today, they're textbook stuff. The universe keeps surprising us, and smart folks have tried and failed to prove time travel's impossible. So never say never. Maybe one day we'll find that exotic matter twist space, time into a loop, or crack the quantum code. Until then, chasing time travel teaches us something profound. The cosmos is a puzzle, and every question we ask pulls us deeper down the rabbit hole. Want to know how the universe works? Keep asking. The answers are out there waiting. So here we are, staring down the cosmic rabbit hole, wondering if we'll ever hold the keys to time's locked doors. Time travel, whether it's skipping to the future on a black hole's edge or dreaming of a wormhole ride to yesterday, isn't just about chasing adventures. It's about asking the big stuff. What is time? Why does it grip us so tightly, pulling us from cradle to grave every step we take toward answering that question? Every paradox we untangle brings us closer to the universe's heartbeat, and maybe it brings us closer to ourselves. Think about it. The universe started with a single perfect note, the Big Bang, a flash of order that's been unravelling ever since. We're part of that song caught in its rhythm, watching stars fade and galaxies drift. Entropy, that relentless push toward chaos, shapes our days. It's why we mourn broken things, why we can't spill the milk. But it's also why we tell stories, build cities, dream of bending time. We're fighting the mess, trying to carve meaning from the scatter. Time travel's the ultimate rebellion, a way to say I'm not done with the past and the future's mine to meet. Yet the universe keeps its cards close. Quantum mechanics teases us with particles that don't care about time's rules, hinting at realities where the past and future dance together. Closed time, like curves, tempt us with loops that could drop us back into yesterday's coffee shop. But even if we cracked those codes, would we like what we find if the block universe is right? Every choice, every tear, every laugh is already etched unchangeable. Time travel might show us the script, but it won't hand us a pen. That's both humbling and thrilling. Our lives are part of a cosmic story, one we're still learning to read. If I could pick a moment to visit, I'd probably sneak into that Roman Colosseum, feel the crowds roar, taste the dust in the air. Or maybe I'd drift back to the universe's first light watch stars kindle in the dark. Honestly, I'd settle for slipping into Hawking's 2009, party just to see his face if someone actually showed up. What about you? Where would you go if time's river let you paddle upstream? The question's not just Phoenix a mirror. It shows us what we value, what we'd fight to relive or reshape. For now, time travel's a spark in the mind, a puzzle physics hasn't solved. But don't bet against it. The universe loves to surprise. What we call impossible today might be tomorrow's. Reality just like radio waves or spaceflight once were. Every question we ask about time, every wild idea about wormholes, black holes or quantum tricks, pushes us to see the cosmos anew. It's not just about building a time machine. It's about understanding the stage we're on. So keep wondering. Keep asking why time flows, why it binds us, why it sets us free. The answers are out there stitched into the stars waiting for us to find them. And who knows, maybe one day we'll raise a glass with Hawking toasting the day we cracked time's code. Imagine a star, a blazing titan in the night sky, living fast and fierce, only to meet its end in a burst so dazzling it outshines entire galaxies. That's a supernova, a cosmic spectacle that doesn't just light up the heavens, but writes the story of life itself. These stellar explosions aren't just fireworks for the universe. They're the forge where the elements of our world, our bodies, our very existence were crafted. To understand a supernova is to trace the thread of our own origins, to see how the death of a star breathes life into the cosmos. Somewhere out there right now, a massive star is taking its final bow. A supernova is the grand cataclysmic finale of a giant star's life, reserved for the heaviest hitters in the stellar lineup. Our sun, it's a modest spark compared to these behemoths, which need to be at least 8 times its mass to go out with such a bang. Look up on a clear night and you might spot one of these giants with your naked eye Betelgeuse, the red supergiant in Orion's shoulder, glowing with a fury that belies its fleeting days. This beast 15 times the mass of our sun could swallow our solar system out to Jupiter's orbit. Yet at less than 10 million years old, it's already on death's doorstep, ready to erupt in a show that could rival the moon's glow for weeks. What drives a star like Betelgeuse to such a dramatic end to unravel that we need to peer into its life, a relentless tug of burnt war between two cosmic forces. Picture a star as a battlefield where gravity pulls inward, squeezing tight while the energy of nuclear fusion pushes back a radiant rebellion against collapse. Deep in a star's heart, atoms slam together, fusing into heavier elements and releasing a torrent of energy. Think billions of atomic bombs detonating every second. This power wants to tear the star apart, but gravity, like a stern overseer, keeps it in check. It's a delicate dance, and for massive stars, it's a sprint, not a marathon. These stellar giants are like cosmic hot rods burning through their fuel at a breakneck pace. For most of their lives, about 90, they fuse hydrogen into helium, a steady churn that keeps them shining. But the bigger the star, the hungrier it is. A supergiant like Betelgeuse guzzles its hydrogen in mere millions of years, not billions like our sun. As the hydrogen dwindles, the star's core feels gravity's grip tighten. The battle shifts and the star fights harder to stay alive, cranking up the heat to fuse helium into carbon. This new phase burns through fuel faster, lasting maybe 1 million years. Then it's onto neon, a process that takes 1,000 years, and silicon, which blazes for just a year. By the time the star's forging iron, it's down to its final day, a frantic cosmic countdown. It's like a chef in a high-stakes cooking show racing against the clock. The star's core becomes a pressure cooker, temperatures soaring to 1 billion degrees, so hot the very idea of heat feels absurd. Each fusion step builds heavier elements, but there's a catch. The heavier the element, the less energy it gives back. Iron's the turning point. Fusing iron doesn't release energy. It steals it like a thief, draining the star's lifeblood. The core, now a massive iron ball, thousands of miles wide, can't fight gravity anymore. The star's been holding back collapse with its fusion fury, but iron tips the scales. Gravity wins and the end is near. This iron core, denser than anything we can imagine, is the star's last stand. As gravity crushes inward, the atoms inside get squeezed tighter and tighter. Electrons buzzing around like frantic bees hate being crowded. Quantum physics steps in demanding they zip faster to avoid each other. Think of a packed stadium where everyone's trying to avoid bumping shoulders. This electron pressure holds the core up, but only for a moment. Soon the iron core starts gobbling up those electrons, merging them with protons to form neutrons. The last defences crumble. In a heartbeat, the core collapses, trillions of tons of iron plummeting inward at 1/4 the speed of light. The star has seconds left to live. Here's where it gets wild. The core's collapse is so fast the star's outer layers don't even have time to catch up. They're left hanging like a cartoon character who hasn't noticed the cliff's gone. Then everything, trillions upon trillions of tons of gas, rushes toward the centre. This catastrophic implosion sets the stage for the supernova's grand exit, a blast so powerful it can outshine a galaxy's worth of stars. But how does a collapse turn into an explosion? That's the mystery astronomers are still chasing, a cosmic riddle that holds the key to the universe's greatest light show. So we've got a star on its last legs, its iron core collapsing faster than a house of cards in a windstorm. Trillions of tons of gas are hurtling inward, racing toward a doomed centre at 1/4 the speed of the light. But here's the head scratcher. How does this catastrophic implosion flip into an explosion so fierce it can outshine a galaxy? That's the cosmic puzzle astronomers have been wrestling with for decades, and it's like trying to figure out how a crumbling building suddenly turns into a fireworks display. The answer lies in the chaos of the stars, final moments where nature pulls off a trick we're still trying to decode. Picture the star's core, now a super, dense knot of neutrons squeezed into a ball just a few miles wide. This is a neutron star in the making, born from the wreckage of the iron core. As the outer layers crash inward, they hit this ultra-dense core and bam! They bounce back like a tennis ball slamming into a concrete wall. This rebound starts a shock wave, a ripple of energy that wants to tear through the star's layers and burst into space. But here's the catch. When scientists crunch the numbers on their supercomputers, that shockwave stalls like a car stuck in the mud. Something's missing, a hidden spark to push it through. Enter the ghost in the machine, neutrinos. These tiny elusive particles are the universe's wallflowers slipping through stars, planets, even us, without so much as a whisper. They're born in the star's collapsing core where protons and electrons smash together to form neutrons spitting out neutrinos in a flood. We're talking trillions of them streaming out with enough energy to make a difference. But neutrinos are shy. They barely interact with anything. Most zip right through the star without a second thought. Yet in the chaos of a supernova, a few get caught in the mix, heating up the gas around the core. It's like tossing a match into a pile of dry leaves, just enough to reignite the fire. But even neutrinos aren't the whole story. The star's not a perfect sphere like some textbook diagram. It's a roiling, turbulent mess. As the shockwave tries to push outward, it stirs up the star's layers, creating hot bubbles that rise and fall like soup boiling over on a stove. This chaos adds energy, turning small ripples into massive waves that slosh through the star. The neutrinos heat, and this turbulent dance team up, giving the shockwave the kick it needs to break free. It's like an interstellar tsunami smashing through the star's outer layers and ripping it apart in a blaze of light. Nature's got this down to an art, even if our computer models are still playing catch up. This moment, the shock breakout, is the star's grand exit. For a fleeting 20 minutes, a flash of light erupts as the shockwave hits the surface brighter than anything else in the sky. Catching it is like spotting a unicorn. In all of astronomy's history, we've only nabbed it twice. Once by NASA's Kepler telescope and once by a lucky amateur in Argentina, Victor Busso. This guy was just snapping photos of a galaxy from his backyard observatory when boom, a star went supernova right in his frame. The odds 1 in 10 million. Victor's pictures caught that first spark the moment the shockwave tore through, and he shared it with the world's astronomers. Talk about a backyard hobby turning into a cosmic win. That flash is just the opening act. The supernova's real show comes from the debris storms of gas and dust blasted into space, glowing for weeks, sometimes months. As the star rips apart, its core becomes a forge fusing elements under insane heat and pressure. Hydrogen, helium, carbon. They smash together, birthing heavier stuff like iron, oxygen, even gold. Some of these elements are radioactive, decaying over time and pumping out light that keeps the supernova shining, long after the initial blast. It's like a celestial firework that doesn't just fizzle out but paints the sky with a lingering glow, outshining billions of stars in its galaxy. This light show isn't just pretty, it's profound. Those elements blasted out by the supernova are the building blocks of everything we know. The iron in your blood, the calcium in your bones, the oxygen you breathe. They were all forged in the hearts of stars that died billions of years ago. Look up at a supernova, and you're seeing your own origin story written in light across the cosmos. That debris doesn't just float away. It seeds the universe, forming clouds of gas and dust that can birth new stars, new planets, maybe even new life. It's a cycle of destruction and creation, a reminder that every end is a beginning. A supernova's glow isn't just a cosmic light show, it's a factory for the stuff of existence. When a star goes out in a blaze, it doesn't just vanish. It scatters its heart across the universe. The intense heat and pressure of the explosion forge new elements, heavy ones like iron, oxygen, sulfur, even the gold in your ring. These aren't just random bits. They're the raw materials for planets, oceans, and life itself. Every atom in your body, from the calcium in your teeth to the carbon in your skin, was born in the fiery death of a star long gone. You're not just stargazing when you look at a supernova, you're meeting your ancestors. This debris flung across space doesn't fade quickly. Radioactive elements cooked in the explosion, decay slowly, fueling a glow that can last months or even years. It's like a firework that lingers, painting the cosmos with shimmering clouds called supernova remnants. These glowing wisps, like the famous Cassiopeia, us, in our Milky Way, are cosmic treasure troves. Cassiopeia, a barely 400 years old, is a young remnant stretching 29 light years wide and still expanding. Thanks to NASA's Chandra X-ray telescope, we've peeked inside and found a jackpot. 70,000 Earths worth of iron and 1 million Earths worth of oxygen. That's enough to build countless worlds, and it's got the building blocks for life itself. Every atom needed for DNA forged in that one stellar blast. Think about that for a second. The iron pumping through your veins, the oxygen filling your lungs. They were crafted in a supernova's furnace billions of years ago. Somewhere eons back, a star exploded, scattering its pieces into a cloud that eventually became our sun, our Earth, us. It's a cosmic hand. Me down a cycle where stars die so others can live. Cassiopeia isn't just a pretty picture in a telescope. It's proof we're all stitched together from stardust, part of a universe that recycles destruction into creation. But not all supernovae play by the same rules. Some stars don't go quietly, they pull stunts that leave astronomers scratching their heads. Take the zombie supernova, a star that seems to die over and over. In 2014, a star in the Great Bear constellation lit up like a supernova, blazing for 600 days. When scientists dug into the records, they found something wild. The same spot had flared up 60 years earlier, and it kept pulsing, brightening and fading 5 times over years. Each burst was supernova, level energy, but the star just wouldn't quit. How does a star pull off multiple deaths? It's like a cosmic cat with 9 lives. The answer lies in its sheer size. Think 100 times the mass of our sun, a monster so massive it's barely holding itself together. Inside, its core reactions go haywire, producing gamma rays, the most intense light in the universe. These rays are so energetic they can turn into matter, throwing the star's balance out of whack. The core starts to collapse, then rebounds, spitting out gas and light in a massive pulse. It's not a full supernova, just a teaser bright enough to fool us. This star pulses, calms down, then pulses again, each time shedding a bit of itself, but not quite exploding. Astronomers still aren't sure if this zombie's finally gone dark or if it's waiting to flare up again next year. Then there's the chameleon supernova SN 2014C, which pulled a fast one on scientists. When it first exploded, it looked like a Type 1 supernova, no hydrogen, in its light signature. But then months later, hydrogen showed up, flipping it to a Type 2. How does a star change its spots? Turns out this star had a wild past. Decades before its Big Bang, it burped out a massive cloud of hydrogen in a smaller eruption. When it finally went supernova, the ejected gases slammed into that old hydrogen cloud, making it glow and turning the star's signature from Type 1 to Type 2. It's like a cosmic costume change, revealing how complex these explosions can be. These oddball zombies, chameleons, show us supernovae aren't one size fits all. Some come from massive stars collapsing under their own weight like Betelgeuse will. Others happen when a white dwarf star steals too much material from a companion and blows up. Each type tells a different story, and every new discovery adds a twist. In 2015, a flash 3.8 billion light-years away looked like the brightest supernova ever, 600 billion times the sun's power. But it wasn't a supernova at all, it was a star shredded by a supermassive black hole stretched like cosmic taffy until it burst. These weird events push our understanding, showing us the universe's extremes are wilder than we ever guessed. Supernovae don't just dazzle, they shape the cosmos. Their shockwaves ripple through space, compressing gas clouds and sparking new stars. Picture a nebula, a vast cloud of gas and dust just hanging out. A nearby supernova's blast can nudge it, squeezing it, until gravity takes over and a new star is born. Our own solar system likely started this way about 4.6 billion years ago. A supernova's shockwave pushed a cloud of dust together, forming our sun and planets. The proof radioactive elements like iron, found in ancient Earth rocks and fossils, only come from supernovae. It's like finding cosmic fingerprints, evidence that a star's death gave our world life. Life, a relentless tug of war between two cosmic forces. Picture a star as a battlefield where gravity pulls inward, squeezing tight, while the energy of nuclear fusion pushes back a radiant rebellion against collapse. Deep in a star's heart, atoms slam together, fusing into heavier elements and releasing a torrent of energy. Think billions of atomic bombs detonating every second. This power wants to tear the star apart, but gravity, like a stern overseer, keeps it in check. It's a delicate dance, and for massive stars, it's a sprint, not a marathon. These stellar giants are like cosmic hot rods burning through their fuel at a breakneck pace. For most of their lives, about 90, they fuse hydrogen into helium, a steady churn that keeps them shining. But the bigger the star, the hungrier it is. A supergiant like Betelgeuse guzzles its hydrogen in mere millions of years, not billions like our sun. As the hydrogen dwindles, the star's core feels gravity's grip tighten. The battle shifts and the star fights harder to stay alive, cranking up the heat to fuse helium into carbon. This new phase burns through fuel faster, lasting maybe 1 million years. Then it's onto neon, a process that takes 1,000 years, and silicon, which blazes for just a year. By the time the star's forging iron, it's down to its final day. Frantic cosmic countdown. It's like a chef in a high-stakes cooking show racing against the clock. The star's core becomes a pressure cooker, temperatures soaring to 1 billion degrees so hot the very idea of heat feels absurd. Each fusion step builds heavier elements, but there's a catch. The heavier the element, the less energy it gives back. Iron's the turning point. Fusing iron doesn't release energy, it steals it like a thief draining the star's lifeblood. The core, now a massive iron ball thousands of miles wide, can't fight gravity anymore. The star's been holding back collapse with its fusion fury, but iron tips the scales. Gravity wins and the end is near. This iron core, denser than anything we can imagine, is the star's last stand. As gravity crushes inward, the atoms inside get squeezed tighter and tighter. Electrons buzzing around like frantic bees hate being crowded. Quantum physics steps in, demanding they zip faster to avoid each other. Think of a packed stadium where everyone's trying to avoid bumping shoulders. This electron pressure holds the core up, but only for a moment. Soon the iron core starts gobbling up those electrons, merging them with protons to form neutrons. The last defences crumble. In a heartbeat, the core collapses, trillions of tons of iron plummeting inward at 1/4 the speed of light. The star has seconds left to live. Here's where it gets wild. The core's collapse is so fast, the star's outer layers don't even have time to catch up. They're left hanging like a cartoon character who hasn't noticed the cliff's gone. Then everything, trillions upon trillions of tons of gas rushes toward the centre. This catastrophic implosion sets the stage for the supernova's grand exit, a blast so powerful it can outshine a galaxy's worth of stars. But how does a collapse turn into an explosion? That's the mystery astronomers are still chasing, a cosmic riddle that holds the key to the universe's greatest light show. So we've got a star on its last legs, its iron core collapsing faster than a house of cards in a windstorm. Trillions of tons of gas are hurtling inward, racing toward a doomed centre at 1/4 the speed of light. But here's the head, Scratcher. How does this catastrophic implosion flip into an explosion so fierce it can outshine a galaxy that's the cosmic puzzle astronomers have been wrestling with for decades, and it's like trying to figure out how a crumbling building suddenly turns into a fireworks display? The answer lies in the chaos of the stars, final moments where nature pulls off a trick we're still trying to decode. Picture the star's core now a super. Dense knot of neutrons squeezed into a ball just a few miles wide. This is a neutron star in the making, born from the wreckage of the iron core. As the outer layers crash inward, they hit this ultra-dense core and bam, they bounce back like a tennis ball slamming into a concrete wall. This rebound starts a shockwave, a ripple of energy that wants to tear through the star's layers and burst into space. But here's the catch. When scientists crunch the numbers on their supercomputers, that shockwave stalls like a car stuck in the mud. Something's missing, hidden spark to push it through. Enter the ghost in the machine. Neutrinos. These tiny elusive particles are the universe's wallflowers, slipping through stars, planets, even us, without so much as a whisper. They're born in the star's collapsing core, where protons and electrons smash together to form neutrons, spitting out neutrinos in a flood. We're talking trillions of them streaming out with enough energy to make a difference. But neutrinos are shy, they barely interact with anything. Most zip right through the star without a second thought. Yet in the chaos of a supernova, a few get caught in the mix, heating up the gas around the core. It's like tossing a match into a pile of dry leaves, just enough to reignite the fire. But even neutrinos aren't the whole story. The star's not a perfect sphere like some textbook diagram. It's a roiling, turbulent mess. As the shockwave tries to push outward, it stirs up the star's layers, creating hot bubbles that rise and fall like soup boiling over on a stove. This chaos adds energy, turning small ripples into massive waves that slosh through the star. The neutrinos heat and this turbulent dance team up, giving the shockwave the kick it needs to break free. It's like an interstellar tsunami smashing through the star's outer layers and ripping it apart in a blaze of light. Nature's got this down to an art, even if our computer models are still playing catch up. This moment, the shock breakout, is the star's grand exit. For a fleeting 20 minutes, a flash of light erupts as the shockwave hits the surface brighter than anything else in the sky. Catching it is like spotting a unicorn. In all of astronomy's history, we've only nabbed it twice. Once by NASA's Kepler telescope and once by a lucky amateur in Argentina, Victor Busso. This guy was just snapping photos of a galaxy from his backyard observatory, when boom, a star went supernova right in his frame. The odds 1 in 10 million, Victor's pictures caught that first spark the moment the shockwave tore through, and he shared it with the world's astronomers. Talk about a backyard hobby turning into a cosmic win. That flash is just the opening act. The supernova's real show comes from the debris stones of gas and dust, blasted into space glowing for weeks, sometimes months. As the star rips apart, its core becomes a forge fusing elements under insane heat and pressure. Hydrogen, helium, carbon, they smash together, birthing heavier stuff like iron, oxygen, even gold. Some of these elements are radioactive, decaying over time and pumping out light that keeps the supernova shining long after the initial blast. It's like a celestial firework that doesn't just fizzle out, but paints the sky with a lingering glow, outshining billions of stars in its galaxy. This light show isn't just pretty, it's profound. Those elements blasted out by the supernova are the building blocks of everything we know. The iron in your blood, the calcium in your bones, the oxygen you breathe. They were all forged in the hearts of stars that died billions of years ago. Look up at a supernova, and you're seeing your own origin story written in light across the cosmos. That debris doesn't just float away. It seeds the universe, forming clouds of gas and dust that can birth new stars, new planets, maybe even new life. It's a cycle of destruction and creation, a reminder that every end is a beginning. A supernova's glow isn't just a cosmic light show, it's a factory for the stuff of existence. When a star goes out in a blaze, it doesn't just vanish. It scatters its heart across the universe. The intense heat and pressure of the explosion forge new elements, heavy ones like iron, oxygen, sulfur, even the gold in your ring. These aren't just random bits. They're the raw materials for planets, oceans and life itself. Every atom in your body, from the calcium in your teeth to the carbon in your skin, was born in the fiery death of a star long gone. You're not just stargazing when you look at a supernova, you're meeting your ancestors. This debris flung across space doesn't fade quickly. Radioactive elements cooked in the explosion decay, slowly fueling a glow that can last months or even years. It's like a firework that lingers, painting the cosmos with shimmering clouds called supernova remnants. These glowing wisps, like the famous Cassiopeia, in our Milky Way, are cosmic treasure troves. Cassiopeia, a barely 400 years old, is a young remnant stretching 29 light-years wide and still expanding. Thanks to NASA's Chandra X-ray telescope, we've peeked inside and found a jackpot. 70,000 Earths worth of iron and 1 million Earths worth of oxygen. That's enough to build countless worlds, and it's got the building blocks for life itself. Every atom needed for DNA, forged in that one stellar blast. Think about that for a second. The iron pumping through your veins, the oxygen filling your lungs. They were crafted in a supernova's furnace billions of years ago. Somewhere eons back, a star exploded, scattering its pieces into a cloud that eventually became our sun. Our Earth, us. It's a cosmic hand, me down a cycle where stars die so others can live. Cassiopeia isn't just a pretty picture in a telescope. It's proof we're all stitched together from stardust, part of a universe that recycles destruction into creation. But not all supernovae play by the same rules. Some stars don't go quietly. They pull stunts that leave astronomers scratching their heads. Take the zombie supernova, a star that seems to die over and over. In 2014, a star in the Great Bear constellation lit up like a supernova, blazing for 600 days. When scientists dug into the records, they found something wild. The same spot had flared up 60 years earlier, and it kept pulsing, brightening and fading 5 times over years. Each burst was supernova level energy, but the star just wouldn't quit. How does a star pull off multiple deaths? It's like a cosmic cat with 9 lives. The answer lies in its sheer size. Think 100 times the mass of our sun, a monster so massive it's barely holding itself together. Inside, its core reactions go haywire, producing gamma rays, the most intense light in the universe. These rays are so energetic they can turn into matter, throwing the star's balance out of whack. The core starts to collapse, then rebounds, spitting out gas and light in a massive pulse. It's not a full supernova, just a teaser bright enough to fool us. This star pulses, calms down, then pulses again, each time shedding a bit of itself, but not quite exploding. Astronomers still aren't sure if this zombie's finally gone dark or if it's waiting to flare up again next year. Then there's the chameleon supernova SN 2014C, which pulled a fast one on scientists. When it first exploded, it looked like a Type 1 supernovano hydrogen in its light signature. But then months later, hydrogen showed up, flipping it to a Type II. How does a star change its spots? Turns out this star had a wild past. Decades before its Big Bang, it burped out a massive cloud of hydrogen in a smaller eruption. When it finally went supernova, the ejected gases slammed into that old hydrogen cloud, making it glow and turning the star's signature from Type I to Type II. It's like a cosmic costume change, revealing how complex these explosions can be. These oddball zombies, chameleons, show a supernova aren't one size fits all. Some come from massive stars collapsing under their own weight like Betelgeuse will. Others happen when a white dwarf star steals too much material from a companion and blows up. Each type tells a different story, and every new discovery adds a twist. In 2015, a flash 3.8 billion light-years away looked like the brightest supernova ever, 600 billion times the sun's power. But it wasn't a supernova at all. It was a star shredded by a supermassive black hole stretched like cosmic taffy until it burst. These weird events push our understanding, showing us the universe's extremes are wilder than we ever guessed. Supernovae don't just dazzle, they shape the cosmos. Their shockwaves ripple through space, compressing gas clouds and sparking new stars. Picture a nebula, a vast cloud of gas and dust just hanging out. A nearby supernova's blast can nudge it, squeezing it until gravity takes over and a new star is born. Our own solar system likely started this way about 4.6 billion years ago. A supernova's shockwave pushed a cloud of dust together, forming our sun and planets. The proof radioactive elements like iron, found in ancient earth rocks and fossils, only come from supernovae. It's like finding cosmic fingerprints, evidence that a star's death gave our world life, and it didn't stop there. About 5 million years ago, a supernova went off close enough to sprinkle iron across Earth, leaving traces in fossils and ocean sediments. Around that time, life on our planet shifted dramatically. Africa's forests gave way to grasslands, species vanished and new ones emerged. Could that supernova have played a role? Its gamma rays, blazing with intense energy, might have zapped Earth's ozone layer, letting more UV radiation pour in. That could have sparked mutations, reshuffling the deck of life from algae to early hominids. It's a wild thought. The explosion of a distant star might have nudged the path that led to us to you listening to this right now. That's the magic of supernova. They're not just explosions. They're architects of existence. They forge the elements that build planets, spark the birth of stars, and maybe even drive the evolution of life. The carbon in your DNA, the oxygen in your breath, it all came from a star that died in a blaze of glory. We're not just connected to the cosmos, we're made of it. Every supernova we study pulls us closer to answering the big questions. Where did we come from and where are we going? These stellar deaths are a reminder that the universe is a cycle of endings and beginnings, and we're part of its story. So here's to supernovas, the cosmic firecrackers that light up the sky and build the worlds below. They're not just dazzling, they're the reason we're here. But let's hope the next one stays far enough away to keep our ozone layer intact. The universe is a wild place, and every supernova is a clue to its secrets. Keep looking up, because those explosions are telling us who we are. Welcome to Endless Universe, where the cosmos whispers its secrets to soothe your mind. I'm your sleep assistant, here to guide you through a gentle journey into the mysteries of the universe. Tonight we drift into the enigma of time before the Big Bang, a realm where clocks never ticked, and existence itself was a silent question. Imagine a vast, endless ocean of nothingness, not dark, not light, just pure potential, waiting to bloom. What was there before the universe sang its first note? Where are you watching from, and what time is it in your corner of the cosmos? If this journey calms your mind, please give it a like, maybe subscribe, and let's keep exploring the stars together. I hope this isn't too fascinating to keep you awake. Picture yourself floating in a soft velvet void, weightless, where the very idea of before feels like a dream. The Big Bang, that grand cosmic spark, 13.8 billion years ago, marks the moment our universe began to write its story. But what came before? Scientists, philosophers and dreamers have long pondered this question, not for answers that shout, but for whispers that comfort. The pre-Big Bang era isn't a place or a time, it's a puzzle wrapped in starlight. To understand it, we must let go of our everyday sense of time, like setting aside a watch that's always ticking. In this cosmic void, there's no morning coffee, no rush to catch a bus. Time as we know it, with its steady march of seconds, didn't exist. Instead, imagine a state of pure possibility, like a blank canvas waiting for an artist's brush. Physicists call this a singularity, a point of infinite density where the rules of space and time dissolve. It's not a dot on a map, but a concept that humbles us. The great mind of Albert Einstein, with his theory of relativity, showed us that time bends and stretches like a river flowing around a stone. Before the Big Bang, there was no river, no stone, just an eternal now. Let's relate this to something familiar. Think of waiting for a kettle to boil, those quiet moments when nothing seems to happen, yet everything is in motion. The pre-Big Bang universe was like that, a stillness pregnant with creation. Ancient Greeks, like the poet Hesiod, imagined a primal chaos, a formless void from which all things sprang. Their myths echo modern science, where the universe's birth wasn't a loud explosion, but a gentle unfolding like a flower opening to the dawn. Now let's sprinkle in a bit of humour. If you've ever felt time crawl during a boring meeting, you've glimpsed a fraction of eternity. The pre-Big Bang state was the ultimate waiting room, no magazines, no clock, just infinite patience. Scientists like Stephen Hawking explored this idea, suggesting time might loop or blur at the universe's edge. His work, built on decades of cosmic curiosity, invites us to wonder without needing every answer. After all, the beauty of the cosmos lies in its mysteries, like a bedtime story that never quite ends. As we drift deeper, consider the elements around you. The carbon in your breath, the calcium in your bones, they were forged in stars, but their story began in that timeless void. You are a piece of the universe, a living memory of its first moments. This connection grounds us like lying on a soft blanket under a starry sky. The pre-Big Bang era, though distant, feels intimate when we realise it's part of us. Let's pause on a cultural note. In ancient Egypt, time was a god named Thoth, weaving order from chaos. Their stories carved in stone remind us that humans have always sought to understand time's birth. Today we use telescopes and equations, but the awe remains. The Hubble Space Telescope, launched in 1990, has peered back nearly to the Big Bang, showing us a light from galaxies born when time was young. Each image is a love letter from the cosmos, inviting us to rest in its vastness. This journey into the cosmic void sets the stage for our exploration. We're not rushing, we're floating, letting the universe's gentle rhythm lull us. The pre-Big Bang mystery is a reminder that some questions are meant to soothe, not solve. As you listen, let your mind soften like waves lapping at a quiet shore. The stars are patient, and so are we, ready to uncover the next whisper of the cosmos. Imagine you're lying on a soft meadow under a sky dusted with stars, each one a quiet promise of something vast. In the moments before the Big Bang, the universe wasn't a roaring symphony, but a delicate whisper, a flicker of possibility in the cosmic dark. These whispers, known as quantum fluctuations, were the seeds from which everything, galaxies, planets, even you, grew. Let's drift into this gentle mystery, where the smallest ripples birthed the grandest story. Quantum fluctuations sound like something from a science fiction novel, but they're as real as the breeze you feel on a cool evening. Picture a still pond, its surface smooth, until a tiny pebble drops, sending ripples outward. In the pre-Big Bang void, the universe was like that pond, not empty but alive with tiny random shifts in energy. These shifts, governed by the strange rules of quantum mechanics, were so subtle, they make a butterfly's wing seem loud. Yet they held the blueprint for creation. Let's make this relatable. Think of baking bread, how a pinch of yeast sparks life in the dough, slowly rising into something warm and whole. Quantum fluctuations were the yeast of the cosmos, invisible but essential. In the 1970s, physicist Alan Guth proposed a theory called inflation, suggesting the universe expanded faster than a heartbeat in its first fraction of a second. Those quantum ripples, stretched by this cosmic growth, became the scaffolding for galaxies. It's like stretching a piece of fabric, revealing patterns woven deep within. Now a touch of humour to keep us grounded. If you've ever tried to predict the weather and failed, you've brushed against the unpredictability of quantum mechanics. These fluctuations weren't planned or orderly. They were the universe's playful doodles scribbled in the margins of eternity. Scientists like Guth, building on the work of quantum pioneers like Werner Heisenberg, showed us that uncertainty isn't a flaw, but a feature of reality. Heisenberg's uncertainty principle, formulated in 1927, tells us we can't know everything about a particle's position and speed. In the pre-Big Bang era, this dance of chance set the stage for time itself. Let's weave in a cultural thread. In Hindu mythology, the god Vishnu dreams the universe into being his breath, creating worlds from chaos. This echoes the quantum whispers where order emerged from randomness. Ancient storytellers didn't have particle accelerators, but their intuition about creation's delicate start feels timeless. Today, experiments like those at CERN's Large Hadron Collider recreate conditions close to the Big Bang, chasing echoes of those first fluctuations. Each discovery is like finding a seashell on a cosmic shore, a reminder of where we began. How does this touch your life? The device you're watching this on, its circuits and chips, relies on quantum mechanics. The same rules that spark the universe power the technology in your hand. It's a quiet miracle, like realizing the stars are distant cousins. The elements in your body, carbon, oxygen, carry the memory of those early ripples forged in stellar furnaces, but rooted in that timeless whisper. You're not just in the universe, you're off-bit, a living echo of its first breath. Let's linger on a historical note. In the 1960s, physicists Arno Penzias and Robert Wilson stumbled upon cosmic microwave background radiation, the faint glow of the Big Bang's afterlight. Their discovery, made with a radio telescope in New Jersey, confirmed that those quantum fluctuations left fingerprints across the sky. Imagine finding an old photograph in your attic, faded but full of stories. This radiation, mapped by satellites like Planck in the 2000s, shows us the universe's baby picture, with patterns tracing back to those pre-Big Bang whispers. As we float through this idea, let's keep it soothing. Picture yourself in a hammock, swaying gently, the night sky above you, a canvas of calm. The quantum fluctuations weren't a storm, but a lullaby rocking the universe into being. They remind us that even the grandest things start small, like a kind word or a fleeting thought. In a world that often feels rushed, there's comfort in knowing creation took its time, unfolding with patience. This exploration of quantum whispers connects to our journey through the cosmic void. Where part 1 invited us to imagine a timeless stillness, here we find the first stirrings the universe's soft inhale before its song began. Scientists continue to probe this mystery, using tools like supercomputers to model those early ripples. Their work, like a poet's pen, seeks beauty in the abstract, offering us a story to dream by. As you listen, let your thoughts drift like clouds across a moonlit sky. The quantum whispers are a reminder that beginnings don't need to be loud to be profound. They're a gentle nudge, inviting you to rest in the wonder of existence. The cosmos is vast, but its secrets are shared in whispers meant to soothe your mind as you sink deeper into this starry tale. Close your eyes and imagine you're drifting on a calm, endless sea, the waves lapping softly against your boat, carrying you nowhere and everywhere. In the story of time before the Big Bang, there's a chapter that feels like this, a universe not born in a single moment, but stretching backward, perhaps forever, in a process called eternal inflation. Let's sail into this tranquil idea, where the cosmos might have no beginning, only an eternal dance of creation. Eternal inflation builds on the inflation theory we touched on earlier, but it's grander, like a symphony that never stops playing. Picture a cosmic bubble bath, each bubble a universe popping into existence and growing endlessly. Our Big Bang 13.8 billion years ago was just one bubble forming in an infinite foam. This idea, proposed by physicist Andre Linde in the 1980s, suggests that inflation, the rapid expansion of space, doesn't end everywhere at once. Instead, pockets of the cosmos keep inflating, spawning new universes, while others like ours settle into being. It's a vision where time might not have a starting line, only an endless horizon. Let's ground this in something familiar. Think of blowing bubbles through a straw into a glass of water. Each bubble rises unique, but the process keeps going as long as you blow. Eternal inflation is like that, a constant creation of universes, each with its own rules, its own time. Linde, inspired by Alan Guth's work, imagined this multiverse as a garden of possibilities, where our universe is one flower among countless others. It's a humbling thought, like realizing your hometown is just one speck on a vast map. Now a dash of humour to keep it light. If you've ever tried to untangle Christmas lights, you know the frustration of endless knots. Eternal inflation is the cosmos's version of that tangle, except instead of lights, it's weaving new realities. Scientists use complex mathematics like equations from quantum field theory to explore this idea. In the 1990s, physicist Alex Vilenkin added to this picture, suggesting that inflation could be self-sustaining, like a cosmic engine that never runs out of fuel. It's a concept that invites wonder, not worry, as we rest in its vastness. Let's weave in a cultural connection. In Buddhist cosmology, the universe cycles through endless births and rebirths, with no fixed start or end. This echoes eternal inflation, where time loops and branches like a river delta. Ancient thinkers without telescopes sensed the cosmos's boundless nature, their stories a soft echo of modern physics. Today, experiments like the Bicep 2 project, which in 2014 searched for gravitational waves from early inflation, try to glimpse this eternal process. Each wave, if found, would be like a ripple from a stone dropped in that cosmic sea long ago. How does this touch your life? The phone in your pocket, the coffee you sip today, they exist because our universe's bubble formed just right. Eternal inflation suggests countless other bubbles where physics might differ, where coffee never brewed. It's a reminder to cherish the delicate balance of our world, like finding the perfect spot to nap on a sunny afternoon. The atoms in your skin, born in our Big Bang, are a unique verse in an infinite poem, connecting you to this grand, timeless tale. Let's linger on history. In the early 20th century, Edwin Hubble's observations showed the universe is expanding, a clue that led to inflation theories. His telescope peering into the night revealed galaxies racing apart like leaves drifting on a stream. This discovery, made in the 1920s at Mount Wilson Observatory, laid the groundwork for understanding inflation's role before our Big Bang. Modern cosmologists, using tools like the Planck satellite map, this expansion, seeking patterns that hint at eternal inflation's endless bubbles. As we float through this idea, imagine yourself in a cozy library, the kind with soft armchairs and the scent of old books. Eternal inflation is a story from that library, one that soothes with its boundlessness. It suggests the universe doesn't need a single birthday, just an eternal rhythm like the rise and fall of your breath. In a world that often demands beginnings and endings, there's peace in imagining something that simply is always unfolding. This chapter flows from the quantum whispers we explored, where tiny ripples set the stage for creation. Now we see those ripples as part of a larger timeless process, one bubble among many. Scientists continue to probe this mystery using supercomputers to simulate inflation's endless dance. Their work, like a painter's brush, adds colour to our understanding, inviting us to dream of universes beyond our own. As you listen, let your mind soften like moonlight spilling across a quiet lake. Eternal inflation is a lullaby of possibility, reminding us that some stories don't need a first page. The cosmos is patient, its bubbles rising and falling in a gentle, endless sea. Let this thought carry you, a soft current guiding you deeper into the starry night. Picture yourself swaying gently in a hammock, the night sky above you, a tapestry of twinkling lights, each star humming a tune too soft to hear. In the mystery of time before the Big Bang, there's a chapter that feels like this, a cosmic dance of invisible strings vibrating in a realm where time itself might dissolve. This is the world of string theory, a poetic idea that reimagines the universe as a symphony of tiny quivering threads. Settle in and let's explore this soothing vision of a cosmos beyond the clock. String theory suggests that the universe's building blocks aren't particles like grains of sand, but minuscule one-dimensional strings smaller than anything we can imagine. These strings vibrating at different frequencies create everything, matter, energy, even gravity, like notes forming a melody. In the pre-Big Bang era, before the Plankipek's first heartbeat, these vibrations might have existed in a timeless state, weaving the fabric of reality. It's a mind-bending idea born in the 1970s from physicists like Gabriele Veneziano, who saw patterns in particle collisions that hinted at something deeper. What's this like in daily life? Imagine plucking a guitar string, how one note can shift from low to high with a gentle twist. String theory says the universe works this way with each vibration, crafting a piece of existence, electrons, photons, or the pull of gravity. In the pre-Big Bang void, these strings might have danced without a stage, no space or time to limit their rhythm. Physicists like Edward Witten in the 1990s unified different versions of string theory into M theory, proposing a cosmos with extra dimensions up to 11 curled up like secrets in a locket. For a bit of humour, think of trying to fold a fitted bedsheet, that impossible tangle of corners. String theory's extra dimensions are like that, folded so tightly we can't see them, yet they shape everything. This theory, still unproven, requires energies far beyond our reach, but experiments at particle accelerators like CERN keep searching for clues, chasing echoes of those ancient vibrations. It's a quest that feels like chasing a dream patient and full of wonder. In ancient Chinese philosophy, the concept of the Tao describes a universal flow, an unseen harmony binding all things. String theory's vibrations resonate with this, suggesting a cosmos united by invisible music. Long before modern physics, such ideas wove through human thought, as if our ancestors heard the universe's hum. Today, supercomputers model these strings simulating conditions before the Big Bang like artists sketching a melody no one's heard but everyone feels. How does this connect to you? The chair you're sitting on, the air you breathe, they're all in theory. Vibrations of cosmic strings tuned just right to form your world. It's like realizing your life is a verse in an endless song, each moment a note born in that timeless dance. The hydrogen in your water, forged in the early universe, carries the echo of those strings, linking you to a symphony older than time. Historically, string theory grew from the 1960s when physicists puzzled over the strong nuclear force. Yoichiro Nambu and others saw string-like behaviours in particles, planting seeds for a revolution. By the 1980s, the first superstring revolution brought new equations showing how strings could unify Einstein's gravity with quantum mechanics. These ideas, debated in university halls from Princeton to Cambridge, are like lanterns lighting a path through the pre-Big Bang dark. Envision yourself in a quiet garden, the air warm, the flowers nodding as if sharing a secret. String theory is that secret, a story of harmony in a universe that seems chaotic. It suggests time might not be a line but a chord struck in a dimension we can't yet see. In a world that often feels fragmented, there's peace in imagining everything connected, vibrating in unison. This chapter weaves from the Planck epoch's first pulse where time began to form. Now we step back, wondering if time itself is just one note in a grander melody. Scientists using tools like gravitational wave detectors seek ripples that might hint at string theory's truth, their work a gentle pursuit of beauty. As you listen, feel your thoughts soften like petals falling on a still pond. String theory's dance is a lullaby inviting you to rest in a universe that sings even in silence. Envision yourself seated by a flickering campfire, the night sky above a canvas of stars, each one a story waiting to be told. Long before telescopes or equations, ancient humans gazed at the heavens, weaving tales to make sense of time's mystery. In our journey through the enigma of time before the Big Bang, this chapter turns to those early dreamers whose myths and musings about eternity echo our modern quest for the universe's origins. Curl up in this moment and let their stories wrap around you like a warm shawl. For ancient cultures, time wasn't a ticking clock, but a living rhythm tied to the cycles of sun, moon and seasons. The Mesopotamians, in the cradle of civilization, 5,000 years ago, saw time as a divine gift shaped by gods like Anu who ruled the sky. Their creation epic, the Enuma Elish, describes a formless chaos before the world, a timeless void where gods battled to bring order. This mirrors our scientific ideas of a pre-Big Bang state where time hadn't yet found its stride. These early thinkers without instruments sensed a cosmos born from stillness, their stories a soft bridge to today's physics. Picture something familiar, the way a river's flow feels eternal yet ever-changing. Ancient Egyptians viewed time this way, as a cycle guided by the god Thoth, who measured days and seasons. Their Book of the Dead speaks of a primeval ocean, none from which all life emerged, a poetic nod to the singularity before the Big Bang. These myths carved in stone along the Nile show how humans have always reached for the timeless-like, stretching toward a star just out of grasp. A bit of humour keeps us grounded. If you've ever lost track of time scrolling through your phone, you've felt a hint of eternity's pull. Ancient people too wrestled with time's vastness, but they turned to stories, not screens. The Babylonians, for instance, tracked stars with clay tablets, creating one of the first calendars. Their priest astronomers, observing from ziggurats, charted cycles that felt infinite, a practice that feels like an ancestor to our cosmic microwave background studies mapping the universe's earliest light. Across the world, India's ancient texts offer another view. The Rig Veda, composed over 3,000 years ago, describes a cosmic hymn, a vibration from which time and space arose. This resonates with string theory's vibrating strings, as if ancient poets and modern physicists heard the same cosmic melody. In the 19th century, scholars like Max Müller translated these texts, revealing their depth to the world. His work, like a lantern in the dark, showed how ancient wisdom aligns with our quest to understand time's birth. How does this touch your life? The calendar on your wall, the holidays you celebrate, they trace back to those early stargazers who gave time its human shape. The iron in your blood, forged in stars, connects you to the cosmos they worshipped. It's like finding an old family recipe, its flavours rooted in a distant past. You carry their curiosity, their awe, every time you wonder about the universe. Historically, the Greeks added their voice. Around 500 BCE, philosopher Anaximander imagined a boundless source, a timeless essence birthing all things. His ideas scribbled in ancient Athens prefigure our notions of a pre-Big Bang void. Centuries later, in the 1600s, Johannes Kepler's laws of planetary motion built on these ancient observations, tying their myths to modern orbits. Today, observatories like ALMA in Chile scan the skies, seeking clues to the universe's infancy, continuing a quest as old as humanity. Imagine yourself in a quiet meadow, the grass soft, the stars above whispering tales of forever. Ancient stories of time's origins are like lullabies, soothing us with their simplicity. They remind us that wonder is timeless, whether told by a fireside or a supercomputer. In a world that hurries, there's comfort in knowing our ancestors paused to dream their thoughts, a gentle thread in the cosmic tapestry. This chapter flows from string theory's cosmic symphony, where vibrations wove reality. Now we see humans weaving their own patterns, finding eternity in the stars. Their myths, like the cosmic background radiation, are echoes of a deeper truth inviting us to rest in their glow. As you listen, let your mind drift like smoke rising from that ancient fire. These stories are a soft cradle rocking you toward dreams where time has no end. Sink into the softness of a quiet evening, the kind where the world feels paused and the stars above seem to hold their breath. In our journey through the mystery of time before the Big Bang, we come to a question that feels both profound and personal. Why does time flow forward like a river carving its path? This arrow of time shapes our lives, and its roots may lie in the timeless void before the universe began. Let's wander into this gentle puzzle, where the cosmos offers clues to soothe your mind. The arrow of time is why we remember yesterday but not tomorrow, why a cup breaks but never unbreaks. Scientists tie this to entropy, a measure of disorder that increases as the universe ages. In the pre-Big Bang era, conditions were so extreme, perhaps a singularity or quantum foam, that time had no direction. When the Big Bang unfolded, entropy began its slow climb like a seed sprouting toward the sun. This gave time its forward march, a one-way street born in the universe's first moments. Imagine a familiar scene, a jigsaw puzzle scattered on a table, pieces chaotic until you start to fit them together. The early universe was like that chaos, a state of low entropy, perfectly ordered in its density. As it expanded, disorder grew, stars formed, galaxies spun, and coffee cooled in your mug. In the 19th century, physicist Ludwig Boltzmann defined entropy, showing why time feels linear. His equations, scratched in Viennese notebooks, suggest the pre-Big Bang state was a blank slate where time could have flowed anyway until expansion chose its path. A touch of humour lightens the mood. If you've ever watched a movie backward, you've seen how odd reverse time feels, people uneating sandwiches, rain falling upward. The arrow of time saves us from that cosmic rewind rooted in the Big Bang's gentle nudge. In the 1960s, physicist Roger Penrose explored this, proposing that the universe's low-entropy start was a cosmic fluke, a gift from the pre-Big Bang void. His work, like a map drawn in starlight, guides us through time's delicate choice. In Mayan culture, time was a sacred cycle marked by calendars carved in stone. Yet their myths also spoke of a primordial chaos, a timeless sea before creation not unlike our scientific singularity. These stories, etched 2,000 years ago, hint at a universal human sense that time's flow began in a shift from stillness. Modern experiments like those studying cosmic microwave background radiation with the Planck satellite confirm this low-entropy start, mapping the universe's first light to trace time's arrow back to its source. How does this shape your world? The memories you cherish, the plans you make, they exist because time moves forward, a legacy of that pre-Big Bang moment. The oxygen you breathe, formed in ancient stars, follows this arrow, carrying you through days and dreams. It's like a journal you write one page at a time, each moment a gift from the cosmos' earliest choice. Reflect on a historical milestone. In the 1920s, Arthur Eddington coined the term arrow of time, linking entropy to our experience of past and future. His lectures delivered in Cambridge wove thermodynamics with philosophy, showing how the universe's expansion tied to the Big Bang set time's course. Today, observatories like LIGO detecting gravitational waves probe ripples from the early universe, seeking clues to why time chose its direction. Picture a serene lake, its surface rippling outward from a single pebble's drop. The arrow of time is that ripple spreading from the Big Bang spark, shaped by the pre-Big Bang void's potential. In a world that often feels rushed, there's solace in knowing time's flow is a cosmic choice, not a demand. This idea, explored by scientists like Sean Carroll in the 21st century, invites us to rest in the universe's patient rhythm. This chapter ties to the ancient stories of time's origins, where myths sensed a shift from chaos to order. Now we see that shift as entropies rise, a scientific echo of those fireside tales. As you listen, let your thoughts drift, like leaves on a stream carried by time's gentle current. The arrow of time is a lullaby singing of a universe that chose to move forward, cradling you in its flow. Settle into the quiet of a starlit night, as if you're resting on a hillside, the cosmos stretching above like a velvet quilt. In our journey through the mystery of time before the Big Bang, we arrive at a realm where time itself seems to pause. Black holes, those enigmatic giants that echo the timeless void of the pre-Big Bang era. Their strange nature offers a window into a universe where clocks falter, inviting us to ponder the edge of time. Let's drift into this cosmic curiosity, where the stars whisper secrets to calm your soul. Black holes are born when massive stars collapse, their gravity so intense that not even light can escape. Within them, time behaves oddly, slowing to a crawl near the event horizon, the point of no return. In the pre-Big Bang singularity, a state of infinite density conditions may have mirrored a black hole's heart, where time and space blur into nothingness. This connection, like a thread woven through the cosmos, suggests black holes are relics of that primordial state, holding clues to time's birth. Think of a familiar moment watching a clock's second hand slow as you daydream. Near a black hole, time dilation, predicted by Einstein's theory of relativity, makes seconds stretch into years for an observer far away. In the 1910s, Einstein's equations scribbled in Berlin revealed how gravity warps time, a truth that resonates with the pre-Big Bang singularity's extreme density. Black holes then are like cosmic mirrors, reflecting the timeless chaos before the Big Bang spark. A bit of humour to keep it light. If you've ever felt time vanish while binge-watching a show, you've grazed a black hole's charm. In the 1970s, physicist Stephen Hawking showed that black holes aren't truly black-leaking energy. Through Hawking radiation, a quantum dance at their edge. This process, theorized in Cambridge, hints that even in the pre-Big Bang void, quantum effects like those we explored earlier may have stirred time's first tick. It's a gentle reminder that even the darkest corners hum with life. In ancient Polynesian myths, the cosmos begins in Po, a vast, formless night where time and light sleep. Black holes with their light-devouring cores feel like echoes of Po, a cultural bridge to our scientific quest. These stories, chanted on Pacific shores centuries ago, capture the awe of a timeless state. Modern observatories like the Event Horizon Telescope, which in 2019 captured a black hole's silhouette, peer into these cosmic voids, seeking answers about time's origins, like sailors navigating by starlight. How does this touch your life? The GPS in your phone guiding you home relies on relativity to account for time's warping near Earth's gravity principles tied to black hole physics. The atoms in your body, born in stellar explosions, may have cousins trapped in black holes linking you to these cosmic enigmas. It's like finding your reflection in a still pond, a quiet connection to the universe's deepest mysteries. Pause for a historical note. In the 1960s, physicist John Wheeler coined the term black hole, giving a name to these invisible giants. His work, building on Einstein and Carl Schwarzschild's 1916 calculations, showed how gravity could collapse time itself. Today, experiments like LIGO, detecting gravitational waves from black hole mergers, ripple back to the pre-Big Bang era, offering clues to a time when all was compressed into a singular point. Envision a tranquil shore waves lapping softly the horizon, blending with the sky. Black holes are like that horizon, a boundary where time softens, echoing the pre-Big Bang void. They remind us that even in the universe's extremes there's a strange calm, a place where questions rest unanswered. Scientists like Andrea Ghez, who mapped black hole orbits in the 1990s, continue this quest. Their discoveries a lullaby for curious minds. This chapter flows from the arrow of time, where entropy set time's course. Now we see black holes as time's edge, where that course falters, tying back to the timeless singularity. As you listen, let your thoughts glide like a boat on a glassy lake, carried by the cosmos's gentle tide. Black holes are a cosmic cradle rocking you toward dreams where time is but a whisper. Picture yourself lying on a soft blanket under a canopy of stars, each twinkling light a doorway to another world. In our exploration of time before the Big Bang, we now step into a breathtaking idea, the multiverse where countless universes exist, each with its own version of time. These realms, born from the same timeless void as our cosmos, offer a glimpse of realities where time might dance to a different tune. Settle into this gentle wonder where the universe feels like a library of endless stories. The multiverse theory suggests our universe is one of many like bubbles floating in a cosmic sea. In the pre-Big Bang era, conditions, perhaps eternal inflation's bubbling foam, could have spawned these parallel realms, each with unique physical laws. In some time might flow backward loop or stand still, unlike our forward-moving arrow. This idea, rooted in quantum mechanics and string theory, gained traction in the 1980s through physicists like Andre Linde, who envisioned a multiverse sprouting from quantum fluctuations, those whispers we explored earlier. Think of a familiar moment flipping through radio stations, each one playing a different song. The multiverse is like that, with each universe tuned to its own rhythm of time. In our universe, the Big Bang set a low-entropy state, giving time its direction. Other universes might have different entropy rules reshaping time's flow. In the 1990s, physicist Max Tegmark proposed a classification of multiverses from those with different constants to those beyond our physics, like a cosmic playlist of infinite tracks. A dash of humour keeps us cosy. If you've ever wished for a redo on a bad day, the multiverse might have a version of you living that perfect moment. In 2003, physicist Brian Greene's work on string theory suggested extra dimensions could host other universes, each a variation on reality. These ideas, though untested, inspire experiments like those at CERN, where particle collisions might hint at other realms, like catching a faint signal from a distant station. In Aboriginal Australian Dreamtime stories, the world exists in a timeless web where past, present and future intertwine. This resonates with the multiverse, where time's rules vary across realms as if the cosmos dreams many worlds at once. These oral traditions, shared for over 60,000 years, echo the multiverse's boundlessness. Modern cosmology, using tools like the Planck satellite studies cosmic microwave background patterns, seeking anomalies that might suggest collisions with other universes like ripples from a neighbouring dream. How does this connect to you, the device you're watching this on its circuits? Humming exists because our universe's physics allow it. In another realm, those rules might falter, and your screen might be a cloud of light. The nitrogen in your lungs forged in our Big Bang ties you to this universe, but the multiverse reminds you that possibility is infinite, like a warm hug from the cosmos. Reflect on a historical note. In the 1950s, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics, suggesting every choice spawns new universes. His ideas, initially dismissed, now fuel multiverse theories debated in lecture halls from MIT to Oxford. Today, gravitational wave detectors like LISA, planned for the 2030s, aim to catch echoes of other universes, continuing a quest that began with Everett's bold vision. Imagine a serene forest moonlight filtering through the trees, each leaf a universe with its own story. The multiverse is that forest, vast and tranquil, where time's variations weave a tapestry of wonder. It suggests our Big Bang was one note in a cosmic chorus born from the same timeless void. In a world that often feels singular, there's peace in imagining countless others, each a soft echo of eternity. This chapter flows from black holes where time slowed at the edge of singularity. Now we expand to a multiverse, where time itself diversifies, rooted in the pre-Big Bang potential. As you listen, let your mind float like a firefly in a summer night, drifting through realms where time bends and sways. The multiverse is a lullaby of possibility, cradling you in a cosmos where every story finds its place. Envision yourself in a cozy attic, rain pattering softly on the roof, a single candle casting a warm glow over old books. In our journey through the mystery of time before the Big Bang, we now turn to the thinkers who wrestled with time's essence, from ancient philosophers to modern physicists. Their ideas, like lanterns in the cosmic dark, illuminate the timeless void before our universe began. Settle into this quiet reflection, where human curiosity weaves a tapestry to soothe your mind. Long before science mapped the cosmos, philosophers pondered time's nature. In ancient Greece, around 400 BCE, Plato described time as a moving image of eternity, a shadow of a changeless realm. His dialogues written in Athens imagined a pre-cosmic state where ideas existed without time's flow, not unlike the pre-Big Bang singularity. Plato's musings shared under olive trees resonate with our quest to understand a universe before clocks where existence was still and whole. Consider a moment from daily life watching clouds drift, their shapes fleeting yet timeless. Aristotle, Plato's student, saw time as the measure of change tied to motion. His writings, penned in the 4th century BCE, suggest a cosmos with no beginning, a cycle without a start. This echoes eternal inflation's endless universes where time might lack a single origin. Aristotle's ideas, debated in ancient lyceums, offer a bridge to our modern puzzles about the pre-Big Bang void. A sprinkle of humour keeps us grounded. If you've ever tried to define now during a long wait, you've tangled with philosophy's riddles. In the 5th century, Augustine of Hippo grappled with time, asking, what was God doing before creation? His answer that time began with the world mirrors our singularity, a point where time emerged. Augustine's Confessions, written in North Africa, feel like a fireside chat, pondering a timeless divine that parallels the pre-Big Bang state. Fast forward to the 20th century, where physicist Stephen Hawking brought philosophy to the cosmos. In his 1988 book, A Brief History of Time, Hawking proposed a no-boundary model where time loops like a sphere's surface with no start or end. This idea, born in Cambridge, suggests the pre-Big Bang era wasn't a void, but a curved dimension like a dream without edges. Hawking's work, blending Einstein's relativity with quantum mechanics, echoes Plato's eternal realm, uniting ancient and modern thought. In Chinese philosophy, Laozi's Tao Te Ching, from the 6th century BCE, describes a formless Tao, a source beyond time. This resonates with Hawking's boundary-free cosmos, as if ancient wisdom and modern physics share a quiet nod. These ideas, whispered through centuries, find echoes in experiments like those at the Large Hadron Collider, probing the universe's earliest conditions to test theories of time's birth. How does this touch your life? The questions you ask. Why does time feel so fleeting carry the same curiosity as Plato's or Hawking's? The calcium in your bones, forged in stars, ties you to the cosmos they studied. It's like holding an old letter, its words still alive. Your existence, shaped by time's flow, is a chapter in their endless dialogue, connecting you to the pre-Big Bang mystery. Reflect on a historical thread. In the 17th century, Isaac Newton saw time as absolute, flowing evenly regardless of events. His Principia, published in 1687, shaped science, until Einstein redefined time as relative. This shift, like a river changing course, led to Hawking's ideas, showing how philosophy and physics intertwine. Today, cosmologists like Lisa Randall explore extra dimensions, seeking time's roots in the pre-Big Bang void. Their work a continuation of ancient debates. Picture a tranquil garden, fireflies blinking in the dusk, each light a thought from a distant mind. Philosophers of time, from Plato to Hawking, are those lights guiding us through the pre-Big Bang enigma. Their questions, gentle and profound, remind us that wonder is universal, whether asked in a Greek agora or a modern lab. In a world that rushes, their reflections offer a pause, a moment to breathe. This chapter flows from the multiverse where time varies across realms. Now we see humans grappling with time's nature, their thoughts a prelude to the Big Bang's spark. As you listen, let your mind drift like mist over a quiet valley, carried by ideas that span millennia. These philosophers are your companions, their voices a lullaby for a night where time feels infinite. Imagine yourself floating in a warm, endless pool, the water cradling you as stars shimmer overhead, each a tiny spark of creation. In our journey through the mystery of time before the Big Bang, we now dive into the universe's smallest pieces, particles and forces that laid the foundation for time itself. These invisible architects dancing in the pre-Big Bang void shaped the cosmos we know. Let's glide into this gentle story where the tiniest things weave the grandest dreams. In the moments after the Big Bang, the universe was a hot, dense soup of fundamental particles, quarks, electrons, photons held together by four forces: gravity, electromagnetism, and the strong and weak nuclear forces. Before the Big Bang, in the Planck epoch's chaotic haze, these forces may have been unified, a single essence, like a seed before a tree. As the universe expanded, this unity splintered, giving time its structure like a river finding its banks. Picture a familiar scene, stirring sugar into tea, watching it dissolve into a swirling dance. Particles in the early universe were like that sugar, moving chaotically, until forces guided them into patterns. In the 1960s, physicist Murray Gell-Mann proposed quarks as the building blocks of protons and neutrons, a theory confirmed by experiments at Stanford's Linear Accelerator. His work, like a map of the subatomic world, suggests that in the pre-Big Bang, singularity particles and forces were so compressed they blurred, waiting for time to emerge. A bit of humour to keep it light if you've ever tried to untangle earbuds you've wrestled with chaos like the early universe's particle soup. In the 1970s, physicists like Sheldon Glashow unified electromagnetism and the weak force into the electroweak force, a step toward understanding the pre-Big Bang unity. Their equations scribbled in Boston labs hint that time's flow began when forces separated like a curtain parting to reveal the stage of existence. In ancient Sumerian myths, the goddess Tiamat's chaotic waters birthed the world when divided by gods. This mirrors the scientific story of particles and forces splitting from a unified state, as if ancient storytellers sensed time's emergence. These tales, etched on clay tablets 4,000 years ago, connect to modern particle accelerators, like CERN's Large Hadron Collider, which recreate the universe's early conditions, seeking the Higgs boson discovered in 2012 that gives particles mass anchoring time's framework. How does this touch your life? The screen glowing before you, the warmth of your breath. These rely on particles and forces born in the Big Bang, rooted in the pre-Big Bang void. The carbon in your skin, formed in stars, is a legacy of those first quarks, like a family heirloom passed through cosmic generations. You're a living mosaic pieced together by the universe's smallest artisans. Reflect on a historical milestone. In the 1930s, Paul Dirac's quantum equations predicted antimatter particles with opposite charges. His work blending relativity and quantum mechanics showed how particles shape reality, even in the pre-Big Bang era's extreme conditions. Today, experiments like those at Fermilab probe antimatter's role in the early universe, seeking why matter survived to form time and space, like uncovering a lost verse in a cosmic poem. Envision a tranquil meadow, fireflies blinking in the dusk, each a particle dancing with unseen forces. These building blocks, though, tiny crafted time's river flowing from the pre-Big Bang chaos. They remind us that even the grandest things galaxies dream start small, like a kind word on a quiet night. Scientists like Peter Higgs, whose 1964 theory predicted the boson, continue this quest. Their discoveries are soft light in the cosmic dark. This chapter flows from the philosopher's musings on time's nature, now grounding those ideas in the particles and forces that birthed it. The pre-Big Bang void, once a philosophical puzzle, becomes a stage for quarks and gluons setting time in motion. As you listen, let your thoughts drift like ripples on a still pond carried by the universe's gentle pulse. These particles are your kin, their dance a lullaby for a night where time feels eternal. Envision yourself in a quiet observatory, the dome open to a sky brimming with stars, their light a silent record of the cosmos's past. In our journey through the mystery of time before the Big Bang, we now turn to the tools, cosmic clocks that scientists use to probe the unmeasurable, the timeless void before our universe began. These instruments, like gentle guides, help us trace the echoes of a time when time itself was unborn. Settle into this serene exploration, where human ingenuity meets the universe's whispers. To study the pre-Big Bang era, scientists rely on tools that peer into the universe's infancy, capturing signals from its earliest moments. The cosmic microwave background, CMB, a faint glow from 13.8 billion years ago, is one such clock, a snapshot of the Big Bang's afterlight. Its patterns, shaped by quantum fluctuations in the pre-Big Bang void, reveal how time and space began to form. Telescopes like the Planck satellite launched in 2009 map this glow, decoding clues about the universe's first breath. Think of a familiar moment, finding an old photograph, its edges faded but full of stories. The CMB is the universe's oldest photo, its light stretched by expansion into microwaves. In the 1960s, Arno Penzias and Robert Wilson accidentally discovered this radiation, their New Jersey antenna buzzing with the cosmos's ancient hum. Their find, a cornerstone of cosmology, connects to the pre-Big Bang state, where fluctuations set the stage for time's emergence like ripples spreading across a still pond. A touch of humour keeps us cosy. If you've ever tried to tune a radio and heard static, you've grazed the CMB's cosmic signal. In the 1980s, physicist George Smoot's COBE satellite refined this discovery, showing tiny temperature variations in the CMB that trace back to the pre-Big Bang quantum whispers. His work, like a painter's delicate brush, revealed the universe's blueprint, helping us measure a time before clocks existed. In ancient Incan culture, the stars were a celestial calendar guiding planting and rituals. Their observatories, like Intihuatana at Machu Picchu, measured time through light and shadow, echoing our modern quest to chart the cosmos. These traditions, carved in stone 500 years ago, align with tools like the Atacama Large Millimeter Array ALMA, which studies early galaxies to understand the conditions following the Big Bang, indirectly probing the pre-Big Bang void. How does this touch your life? The phone you're using, its GPS ticking in sync with atomic clocks, owes its precision to the same physics that studies the CMB. The oxygen in your lungs, born in ancient stars, carries the legacy of that early light, linking you to the cosmic clocks we measure. It's like holding a seashell to your ear, hearing the universe's distant song in your everyday moments. Reflect on a historical milestone. In the 1910s, Vesto Slipher's observations of galaxy redshifts hinted at the universe's expansion, a clue to its origins. His work conducted in Arizona laid the groundwork for CMB studies showing how light carries time's story. Today, experiments like the Simons Observatory in Chile search for gravitational waves in the CMB ripples from the pre-Big Bang era's inflation, like echoes of a cosmic heartbeat. Picture a tranquil lake at dawn, its surface reflecting the first light, each ripple a moment preserved. Cosmic clocks like the CMB are that lake capturing the pre-Big Bang void's faint traces. They remind us that even the unmeasurable can be touched like a memory held close. Scientists like those at the BICEP project continue this quest. Their telescopes a bridge between human curiosity and the cosmos's quiet truths. This chapter flows from the particles and forces that shaped time, now focusing on how we measure their legacy. The pre-Big Bang void, once a theoretical shadow, becomes visible through these tools grounding philosophy and observation. As you listen, let your thoughts drift like clouds across a moonlit sky carried by the gentle rhythm of discovery. These cosmic clocks are your companions, their steady hum, a lullaby for a night where time feels boundless. Picture yourself nestled in a soft armchair by a window, the night outside alive with stars each one, a tale spun by ancient voices. In our journey through the mystery of time before the Big Bang, we now listen to the world's creation myths, stories that capture the timeless void before the cosmos began. These narratives, woven by cultures across millennia, echo the scientific quest to understand time's birth, offering comfort like a familiar lullaby. Lean into this gentle tapestry, where human imagination meets the universe's deep truths. Across the globe, creation myths often begin with a formless void, a timeless state before light or time. In the Yoruba tradition of West Africa, the universe starts with Oloran, the sky god shaping the world from a watery chaos. This primal stillness, told through oral stories over 2,000 years, mirrors the pre-Big Bang singularity where time waited to unfold. These tales shared under baobab trees carry a universal awe, as if humanity sensed the cosmos's silent beginning. Imagine a moment from your life, the hush before a storm when the air feels heavy with possibility. In Japanese Shinto mythology, the Kojiki describes a chaotic sea before the gods Izanagi and Izanami stir the world into being. This formless start, written in the 8th century, feels like the quantum fluctuations before the Big Bang, a cosmic breath, before time's first step. These stories, chanted in ancient shrines, weave a thread to our modern telescopes, scanning the skies for that first light. A dash of humour to keep it warm. If you've ever tried to start a story and stared at a blank page, you've felt the void of creation myths. In the Maori tradition of New Zealand, the world begins in the embrace of Rangi Sky and Papa Earth. A timeless unity before their separation births time. These oral tales, shared for over 1,000 years, resonate with the Planck epoch's unified forces, a reminder that even science and myth dream of beginnings. In Norse mythology, the Ginnungagap, a yawning gap between fire and ice sparks creation, a story sung by skalds 1,000 years ago. This echoes the pre-Big Bang state's extreme conditions where opposites merge to birth time. In the 19th century, scholars like Jacob Grimm collected these myths, showing their depth to the world. Modern cosmology, with tools like the James Webb Space Telescope, launched in 2021, peers back to the universe's infancy-seeking light that carries these ancient echoes like a song from a distant shore. How does this touch your life? The holidays you celebrate, the seasons you mark, they draw from these myths, tying your days to stories of time's birth. The hydrogen in your water, forged in the Big Bang, connects you to the chaos these tales describe, like a family tree rooted in the stars. You carry their wonder, a quiet link to ancestors who gazed at the same sky, pondering the same mysteries. Reflect on a historical thread. In the 18th century, European scholars like Giambattista Vico studied global myths, noting their shared themes of chaos and creation. His work, published in Naples, laid groundwork for comparative mythology, linking ancient stories to modern science. Today, anthropologists and cosmologists collaborate, exploring how myths like the Aboriginal Dreamtime with its timeless web align with multiverse theories, creating a dialogue between story and starlight. Envision a tranquil beach waves whispering against the shore, each crest a myth from a distant land. Creation stories are those waves carrying the pre-Big Bang void's essence across cultures. They remind us that humans, whether by firelight or satellite, seek meaning in the timeless quest as soft as a sigh. These tales, like the cosmic microwave background's glow, are relics of our shared curiosity, inviting us to rest in their embrace. This chapter flows from the cosmic clock's measuring time's origins, now turning to myths that sense those origins without instruments. The pre-Big Bang void, probed by science, lives in these stories, uniting telescope and tale. As you listen, let your thoughts drift like petals on a breeze carried by voices from every corner of the earth. These myths are your cradle, rocking you toward dreams where time is a story forever unfolding. Close your eyes and feel the gentle rhythm of your breath. Each inhale a quiet gift from the cosmos, each exhale a note in its endless song. In our journey through the mystery of time before the Big Bang, we now turn inward to the stardust that forms you, a living echo of the timeless void before the universe began. Your body, your thoughts, your very being are woven from the pre-Big Bang's potential, tying you to the stars. Rest in this intimate truth where the cosmos lives within you. Every atom in your body, carbon in your skin, oxygen in your lungs, calcium in your bones, was forged in stars, but their story begins in the pre-Big Bang era. The quarks and electrons that make you were once part of that singular timeless state, a cosmic seed waiting to bloom. When the Big Bang sparked, those particles danced through eons, shaping galaxies, planets, and eventually you. You're a walking relic of that primordial moment, a piece of the universe gazing back at itself. Think of a familiar comfort, sipping warm tea, its heat spreading through your hands. That warmth, driven by molecular motion, traces back to the energy of the Big Bang, rooted in the pre-Big Bang void's quantum fluctuations. In the 1940s, chemist Carl Sagan popularized the idea that we are made of star stuff, a poetic truth grounded in physics. His words shared on television remind us that the pre-Big Bang potential lives in every cell like a memory held close. A touch of humor to keep it light. If you've ever felt like you're carrying the weight of the world, you're literally made of cosmic leftovers. In the 1980s, astrophysicist Neil deGrasse Tyson expanded on this, explaining how supernovae scattered elements across space elements now in your blood. These insights, drawn from telescope data, connect the pre-Big Bang singularity to your heartbeat, a rhythm born when time first stirred. In Native American Cherokee stories, the world begins with a great buzzard shaping the earth from a formless void, its wings stirring life. This echoes the scientific tale of particles coalescing from the pre-Big Bang, chaos forming you over billions of years. These oral traditions passed down for centuries resonate with modern biology, which traces human DNA to ancient stardust. Experiments like those at the European Southern Observatory, studying star-forming regions, confirm this cosmic lineage linking myth to molecule. How does this shape your life? The phone in your hand, the chair you sit on, they're made of the same stardust, but you're alive, thinking, dreaming. The nitrogen in your muscles, forged in stellar furnaces, carries the pre-Big Bang's legacy, making every step a cosmic journey. It's like finding an old journal, its pages written in starlight, each word a moment of your existence tied to the universe's dawn. Pause for a historical note. In the 1920s, Cecilia Payne-Gaposchkin's research at Harvard revealed that stars are mostly hydrogen and helium elements born in the Big Bang. Her work, initially overlooked, showed how these elements formed heavier ones like the carbon in your body. Today, missions like the Gaia telescope map stars' compositions, tracing their origins to the pre-Big Bang void, a scientific ode to your cosmic roots. Picture a quiet forest. Sunlight filtering through leaves, each ray a thread from the stars. You are that forest, your cells, a living archive of the pre-Big Bang era. This truth invites peace, reminding you that you belong to the cosmos as natural as a wave on a shore. Scientists like those studying nuclear synthesis continue to unravel how elements form their work, a gentle bridge between you and the universe's first spark. This chapter flows from the creation myths that sense time's birth, now grounding that wonder in your own body. The pre-Big Bang void, once a distant mystery, becomes personal, its particles pulsing in your veins. As you listen, let your thoughts soften like moonlight on a still lake, carried by the realization that you are the universe's story, alive and breathing. This stardust is your home, a cradle rocking you toward dreams where you and the cosmos are one. Imagine yourself lying on a soft hillside, the grass cool beneath you, the night sky, a blanket of stars stretching into forever. We've journeyed through the enigma of time before the Big Bang, a timeless void where the universe held its breath waiting to sing. From quantum whispers to ancient myths, from black holes to the stardust in your veins, we've woven a tapestry of wonder, each thread a gentle invitation to rest. As we close this cosmic tale, let your mind drift cradled by the universe's quiet embrace. Our voyage began in the cosmic void, a stillness where time was but a dream. We floated through quantum fluctuations, those delicate ripples that sparked existence, and sailed across eternal inflation's bubbling realms. The Planck epoch's first heartbeat pulsed string theory's vibrations, hummed, and ancient minds wove stories of eternity. We followed the arrow of time's forward flow, peered into black holes' timeless edges, and wandered the multiverse's varied clocks. Philosophers from Plato to Hawking shared their musings while particles and forces built time's foundation. Cosmic clocks like the microwave background's glow measured the unmeasurable, and global myths echoed the void's mystery. Finally, we found time in you, your body a living echo of that pre-Big Bang potential. Each chapter, like a star in a constellation, connects to form a story that soothes. The pre-Big Bang era, once a distant puzzle, feels close when we see its traces in our breath, our dreams. Science and myth tools and tales blend in this journey, reminding us that the universe is patient, its secrets shared in whispers meant to calm. The quarks in your cells, the light in your eyes, they carry the legacy of a time before time, a truth as comforting as a familiar song. Reflect on a moment from your day, the warmth of a loved one's smile, the rustle of leaves in the wind. These too are gifts of the cosmos born from that timeless void. In Hindu mythology, the god Brahma dreams the universe each cycle a breath of creation. Our journey mirrors this, a dreamlike exploration of time's birth, inviting you to rest in its rhythm. Modern science, with telescopes like Hubble and equations from Einstein, continues this dream, mapping a cosmos that began in silence. Where are you watching from, and what time is it in your corner of the cosmos? If this journey has eased your mind, please give it a like, maybe subscribe, and let's keep exploring the stars together. Your presence, whether in a bustling city or a quiet village, is part of this cosmic story, a note in its endless melody. Picture a serene river, its current soft, carrying you towards sleep. The pre-Big Bang mystery is that river, its flow, a reminder that some questions are meant to comfort, not solve. You are the universe's child, your existence a spark from that timeless void, your dreams a canvas for its wonders. Scientists and storytellers from ancient firesides to modern labs share this truth: the cosmos is vast, but it holds you close. As you drift, let the stars above become fireflies, their light a gentle guide. The pre-Big Bang era, with its quantum seeds and mythic echoes, is a lullaby rocking you into peace. Time, whether measured by clocks or felt in your heart, is a gift from that first spark. Let your thoughts soften like petals falling on a quiet pond, and surrender to the universe's embrace. Sleep well, and may your dreams drift among the stars. Extended reflection for length. To linger in this closing, consider the tools that brought us here. The Planck satellite's maps, the Large Hadron Collider's collisions, the oral tales of the Maori, they're all lanterns lighting the path to the pre-Big Bang void. In the 1970s, physicist John Wheeler's work on quantum foam suggested a universe bubbling with possibility of vision that ties to your own creativity, your ability to imagine and dream. His ideas, like those of ancient poets, remind us that the cosmos is a story we all share. Think of a childhood memory chasing fireflies, their glow, fleeting but magical. The pre-Big Bang era is that glow, elusive yet ever-present in the atoms of your body. The iron in your blood, forged in stars, carries the memory of that timeless state, a quiet link to eternity. In a world that often hurries, this connection offers solace, a moment to pause and breathe. The universe, with its 13.8 billion years, is patient, and so are you, resting now in its vastness. The pre-Big Bang mystery, explored through science and story, is a reminder that beginnings are soft like the first light of dawn. As you sink deeper, let the cosmos cradle you, its secrets a gentle hum. This journey from void to stardust is yours, a cosmic tale to carry into sleep. Welcome to Endless Universe, where the cosmos whispers its secrets to soothe your mind. I'm your sleep assistant here to guide you through a gentle journey into the mysteries of the universe. Tonight we're drifting toward a question as timeless as the stars: how are galaxies and planets born? Imagine vast clouds of gas and dust swirling in the darkness, slowly knitting themselves into the glowing spirals of galaxies and the quiet spheres of planets. It's a story of creation, a cosmic lullaby written in stardust and sung across billions of years, inviting you to rest as you listen. Where are you watching from, and what time is it in your corner of the cosmos? Are you curled up under warm blankets with a cup of tea nearby, or perhaps gazing out at a starry sky from a quiet corner of the world? Let me know in the comments if you're still awake by the end. If this journey calms your mind or sparks a quiet wonder, I'd be ever so grateful if you gave this video a like, maybe tapped subscribe, and joined our little community of cosmic dreamers. It helps others find this tranquil corner of the universe where curiosity meets rest. Now, I hope this tale isn't so fascinating that it keeps you awake, but if it does well, at least you'll have learned something about the birth of everything before you drift off. Picture the universe as a vast quiet nursery not filled with cribs or blankets, but with gas dust and infinite possibility. Galaxies, those grand glittering cities of stars and planets, those humble worlds that spin silently in their orbits, all begin somewhere. But where? How does nothingness become something? How does the void give birth to the swirling arms of the Milky Way, or the rocky cradle of Earth? It's a process so slow, so patient, that it feels like the universe is taking its time, carefully crafting each star, each world, like an artist shaping clay under starlight. To understand this cosmic birth, we need to go back, way back to a time before galaxies, before planets, before even the stars themselves. The universe in its infancy was not a place of structure or form. It was a sea of energy, hot and chaotic, with no up, no down, just an endless expanse of potential. From this formless beginning, the seeds of galaxies were sown tiny ripples in the fabric of space that would grow into the vast structures we see today. Planets too have their origins in this cosmic dawn, but their story is more intimate, tied to the lives of stars and the dusty disks that swirl around them. It's a tale of gravity's gentle pull of particles finding each other in the dark of chaos, giving way to order. What does birth mean in the cosmic sense? On Earth we think of birth as a moment, a spark, a breath, a beginning. But in the cosmos, birth is a process unfolding over eons, so gradual, it's almost imperceptible, like a dream taking shape in the quiet of night. Galaxies don't burst into being. They gather layer by layer as gravity weaves threads of gas and dust into tapestries of light. Planets don't simply appear. They coalesce grain by grain in the warm embrace of a star's gravity. It's a process that feels almost alive, as if the universe is breathing, expanding and creating with every moment that passes. This idea of cosmic creation has captivated humans for millennia. Ancient cultures looked to the skies and saw stories of gods and giants, weaving myths to explain the stars and worlds above. The Babylonians spoke of Marduk shaping the heavens. The Norse saw the cosmos as a great tree Yggdrasil holding worlds in its branches. The Aboriginal peoples of Australia told of the dreamtime when ancestral beings shaped the land and sky. Even today, with our telescopes and equations, we're still chasing that same question: how does it all begin? Science gives us answers, but the wonder remains as timeless as the stars themselves. Let's linger on this idea of cosmic birth a little longer. It's not just the creation of something new, it's the transformation of what already exists. The universe doesn't start from nothing, it reshapes itself, recycling energy, matter and time into new forms. The hydrogen and helium that formed the first galaxies were born in the fiery crucible of the Big Bang. The dust that became planets was forged in the hearts of ancient stars. Everything in the cosmos is connected, a grand cycle of creation and rebirth that stretches across billions of years. This cycle is what makes the story of galaxies and planets so compelling. It's not just about distant objects in the sky, it's about us too. The elements in your body, carbon, oxygen, iron, were once part of stars that lived and died long before Earth was born. You are in a very real way a piece of the cosmos, a fragment of stardust that has journeyed through time to become you. And that's what we'll explore in this video, the slow, beautiful process that turns chaos into galaxies, dust into planets and the universe into a place where life can dream. Our journey will take us from the universe's first moments to the quiet formation of planets like our own. We'll wander through clouds where stars are born, disks where planets take shape, and the forces that sculpt galaxies into their majestic forms. It's a story that's both vast and intimate, distant and close to home, like looking at a starry sky and feeling it's part of you. So let's begin drifting into the cosmos where galaxies and planets are born one quiet moment at a time. This is just the beginning, a gentle step into a story that spans billions of years and countless worlds. As we move forward, we'll unravel the science, the history and the poetry of cosmic creation. For now, rest easy, knowing that the universe is always building, always dreaming, always spinning new stories in the dark. You, dear traveller, are part of that story, a tiny spark in the endless universe, listening to its whispers as you drift towards sleep. To understand how galaxies and planets are born, we must travel back to the very beginning, to a moment when the universe itself took its first breath. Imagine a point smaller than a grain of sand, hotter than 1,000 suns, containing all the energy, matter and possibility that would ever exist. This is the Big Bang, the cosmic spark that set everything in motion, the opening note of the universe's grand symphony. It's not an explosion in the way we think of fireworks or bursting balloons, but a rapid expansion, a stretching of space itself unfolding like a flower in the darkness, spreading light and potential across the void. This is where the story of galaxies and planets begins, in a moment so distant yet so close, for every star, every world, every breath you take traces back to this singular event. Let's picture the universe in its earliest moments, a sea of searing energy too hot for anything familiar to exist. There were no stars, no galaxies, no planets, just a plasma of energy and particles buzzing with unimaginable heat. The temperature was billions of degrees of furnace where even atoms couldn't hold together. Space itself was expanding, stretching like dough rising in a warm oven, carrying this primal soup farther and wider with every passing instant. In these first fractions of a second, the universe was a place of pure potential, a blank canvas waiting for the brushstrokes of creation. It's hard to imagine, isn't it? A time before time, a place before places, yet this is where the seeds of every galaxy and planet were sown. This early universe wasn't calm or orderly. It was chaotic, a swirling mix of particles and radiation with no structure to speak of. But something remarkable happened in those first moments, a process called cosmic inflation. Scientists believe that for a tiny sliver of time, less than a trillionth of a second, the universe expanded faster than light itself, ballooning from smaller than an atom to the size of a grapefruit, or perhaps larger in an instant. This rapid stretch smoothed out the universe, flattening its wrinkles like a sheet pulled tight across a bed, creating a near-uniform canvas of space. Yet within this smoothness, tiny imperfections remained like ripples on a quiet pond, and these ripples would become the blueprints for galaxies. These imperfections, known as quantum fluctuations, were minuscule variations in density, born from the uncertainty of the quantum world. Some regions of the early universe were ever so slightly denser than others, like patches of fog a bit thicker in a misty morning. Over time, gravity would tug at these denser spots, pulling matter together, setting the stage for the first structures to form. It's as if the universe planted tiny seeds in its own fabric, seeds that would grow into the vast galaxies we see today, each one a glittering city of stars. These fluctuations were so small that they seem insignificant, yet they were the sparks that ignited the creation of everything we know. As the universe expanded and cooled, it began to take on a form we can start to recognize. Within the first second after the Big Bang, the searing plasma began to settle. Protons and neutrons formed, combining into the simplest elements, hydrogen and helium, the building blocks of stars. These elements were like the first ingredients in a cosmic recipe, simple but essential, ready to be cooked into galaxies and planets over billions of years. The universe was still too hot for atoms to fully form, but the foundations were there, floating in a vast cooling sea of light and matter. This early universe was bathed in light, a glow so intense it's hard to fathom. Photons, those tiny packets of energy, bounced endlessly between particles, creating a fog that made the cosmos opaque, like trying to see through a thick, radiant mist. For nearly 380,000 years, this fog persisted, until the universe cooled enough for electrons to join protons, forming neutral atoms. This moment, called recombination, was when the universe became transparent, like a curtain lifting to reveal the stage. Light was finally free to travel, and the photons from this era still drift through space today, forming the cosmic microwave background, a faint whisper of the Big Bang's first light. This cosmic microwave background is like a snapshot of the universe's infancy, a map of those tiny density fluctuations frozen in time. Scientists study it with telescopes, piecing together the story of how the universe began. Those denser patches, those seeds of creation, were where matter began to clump under gravity's gentle pull. Over millions of years, these clumps would grow, drawing in more gas and dust, forming the first stars and galaxies. It's a slow process, like watching a river carve a canyon, but it's relentless, driven by the quiet persistence of gravity. The Big Bang wasn't just the birth of the universe, it was the birth of possibility. The hydrogen and helium it created would become the raw materials for stars, which in turn would forge the elements needed for planets. The tiny ripples it left behind would shape the vast structures of galaxies, each one a cosmic tapestry woven from countless threads of light and matter. It's a story that feels almost personal, doesn't it? The atoms in your body, the carbon in your skin, the oxygen in your breath, all began in this fiery moment billions of years ago in a universe that was just learning to dream. This connection to the Big Bang makes the birth of galaxies and planets more than a scientific tale. It's a story of belonging. Every star in the sky, every planet orbiting a distant sun is a descendant of that first spark. And so, are you a tiny piece of the cosmos listening to its story as you drift in the quiet of night? The universe in its earliest moments was setting the stage for everything that would follow, from the swirling arms of the Milky Way to the gentle spin of Earth. It's a grand beginning, but a humble one too, built from the simplest ingredients and the softest ripples. As we drift further into this journey, we'll see how those ripples grew into clouds, how clouds became stars, and how stars gave birth to planets. For now, let's rest in the glow of that first moment when the universe was young, when everything was possible, and when the seeds of galaxies and planets were just beginning to take root. You're part of this story, a quiet spark in the endless universe, carried along by the same forces that shaped the cosmos, dreaming under the same ancient light. As the universe cooled and stretched after the Big Bang, its chaotic energy began to settle into something softer, more delicate. Imagine a vast dark canvas, still warm from its fiery birth, now dotted with faint wisps of gas and dust, drifting like mist over a quiet lake. These wisps were the first molecular clouds, the cosmic nurseries where the seeds of galaxies and stars would take root. They weren't grand or glowing, not yet, but they held the promise of creation like a handful of clay waiting for an artist's touch. In these gentle clouds, the universe began to weave its first structures, setting the stage for the birth of galaxies, and eventually the planets that would orbit their stars. It's a story of patience, of quiet gathering, and of the universe learning to build. Picture these molecular clouds, vast and sprawling, stretching across light years, yet so thin you could hardly see them against the darkness. They were made mostly of hydrogen and helium, the simple elements born in the Big Bang's crucible, with traces of dust, tiny grains of carbon, silicon and ice forged in the hearts of the earlier stars that had already lived and died. These clouds weren't static. They moved swirling gently in the cosmic currents nudged by gravity and the faint ripples left from the universe's infancy. Some were small, destined to birth a single star, while others were enormous, holding enough material to form entire clusters, the building blocks of galaxies. These clouds were cold, far colder than anything we know on Earth, hovering just above absolute zero where warmth is but a memory. In this chill, molecules could form hydrogen atoms pairing up to create delicate bonds, cooling the gas further, making it denser and more ready to collapse. It's as if the universe was whispering to itself, coaxing these clouds into creation, like a gardener tending to fragile sprouts. This cooling was vital, for only in dense, cool clouds could gravity work its magic, pulling particles closer, tightening the threads of matter into knots that would one day ignite as stars. Gravity, that quiet architect, was the key to this transformation. In those denser patches where the Big Bang's ripples had left a little extra matter, gravity began to tug ever so gently, like a parent guiding a child's first steps. Over millions of years, these patches grew, drawing in more gas and dust, becoming denser, still like snowflakes piling into a snowball rolling down a hill. As they grew, the clouds began to fragment, breaking into smaller clumps, each a potential stellar nursery, a cradle where stars and later planets would be born. It's a slow dance, one that takes eons, but it's relentless, driven by the universe's deep desire to create. These stellar nurseries weren't empty or lifeless. They were alive, with motion, with energy, even in their cold silence. Within them, turbulence stirred the gas, creating swirls and eddies like cream mixing into a cup of tea. Magnetic fields threaded through the clouds, guiding the flow of particles shaping their collapse. Sometimes shockwaves from nearby stars, those early giants that exploded as supernovae swept through, compressing the gas, sparking new collapses. It's as if the universe was playing a cosmic game of dominoes where one star's death could trigger the birth of many more. Let's linger in one of these nurseries for a moment, imagining a cloud so vast it could swallow our solar system 1,000 times over. Deep within a dense core forms a knot of gas and dust no larger than a city yet heavy with potential. This core is the embryo of a star, a protostar glowing faintly with the heat of its own compression. Around it, the cloud continues to swirl a disk of leftover material that might one day become planets. This is where galaxies begin to take shape, not as single stars, but as clusters, as families born together in these cosmic cradles. The birth of these first stars was a turning point for the universe. Before them, the cosmos was dark, a place of gas and silence, lit only by the faint glow of the cosmic microwave background. But when these stars ignited, fusing hydrogen into helium in their cores, they brought light to the darkness, like candles flickering in a vast empty room. These were no ordinary stars. They were massive, hundreds of times heavier than our sun, burning hot and fast, living only a few million years before exploding in brilliant supernova. Their death scattered new elements, carbon, oxygen, iron, into the surrounding clouds, enriching them for future generations of stars and planets. These early stars didn't form alone. In the densest clouds, hundreds or thousands ignited together, creating the first star clusters, the seeds of galaxies. Over time, these clusters merged, drawn together by gravity, forming larger structures. Irregular galaxies, small and chaotic, but the ancestors of the grand spirals and ellipticals we see today. It's as if the universe was sketching its first rough drafts, experimenting with shapes and sizes, learning how to build the cosmic cities we call galaxies. This process wasn't just about stars. It was about setting the stage for planets too. The disks of gas and dust around those early protostars were the precursors to planetary systems. Within them, tiny grains of dust began to stick together like snowflakes, forming in a winter storm, growing into the seeds of worlds. These disks were the universe's first workshops where the raw materials of planets, rock, ice, and gas began to take shape. It's a humbling thought, isn't it? The same clouds that birthed galaxies also held the potential for planets, for worlds where life might one day dream. The story of these molecular clouds is one of transformation, of turning the simple into the complex, the formless into the formed. They remind us that creation is a patient process, not a single moment, but a series of quiet steps, each building on the last. The hydrogen in those clouds, born in the Big Bang, would become the fuel for stars. The dust forged in stellar hearts would become the stuff of planets, and the galaxies they formed would become the homes for countless worlds, each one a tiny spark in the cosmic tapestry. As we drift through this story, let's carry the image of these clouds, vast and cold yet brimming with life. They're the universe's nurseries, where galaxies and planets begin, where chaos becomes order, and where the dark gives way to light. You too are part of this creation, made from the same stardust, listening to the same cosmic lullaby that began billions of years ago. Rest easy knowing that the universe is still weaving its clouds, still dreaming its stars, still crafting its worlds one gentle swirl at a time. In the vast, quiet expanse of the early universe, where molecular clouds drifted like mist across a darkened sea, one force began to work its silent magic: gravity. Imagine gravity as a gentle hand reaching out across the cosmos, coaxing particles of gas and dust to come closer together, to weave themselves into something new. It's not a loud or forceful presence, not like the winds that sweep across Earth's plains, but a patient, persistent pull, as steady as a heartbeat. This force, so subtle yet so powerful, is the architect of galaxies and the sculptor of planets, turning the formless clouds of the universe's infancy into the glowing structures we see today. It's the story of how chaos becomes order, how the scattered becomes the whole, and how the universe builds its wonders, one gentle tug at a time. Let's picture those early molecular clouds, vast and cold, floating in the darkness like wisps of fog on a winter morning. Within them, the tiny density fluctuations from the Big Bang, those ripples in the cosmic fabric, created pockets where matter was just a little denser, like a slightly thicker patch of mist. Gravity, ever attentive, noticed these pockets and began its work. It pulled particles closer, not in a rush, but with a quiet insistence, like a parent gathering scattered toys into a neat pile. Over millions of years, these denser regions grew, attracting more gas, more dust, more of the universe's raw materials until they became the seeds of something grander. This process wasn't uniform across the cosmos. In some regions, the clouds were massive, holding enough material to birth entire galaxies, collections of millions or billions of stars bound together by gravity's embrace. In others, smaller clumps formed, destined to become individual stars or clusters, each a potential cradle for planets. Gravity didn't discriminate. It worked the same everywhere, pulling matter together with the same steady rhythm like a weaver threading a loom. The denser the clump, the stronger gravity's pull became, creating a feedback loop where more matter meant more attraction, and more attraction meant more matter, like a snowball rolling down a cosmic hill. As these clouds collapsed under gravity's influence, they didn't just shrink, they transformed. The gas and dust pressed closer, heating up as particles collided, like the warmth you feel when you rub your hands together on a cold day. In the densest cores, this heat sparked the birth of stars, their fusion igniting like a candle in the dark. But gravity's role didn't end there. Around these newborn stars, the leftover gas and dust began to swirl, forming spinning disks like water circling a drain. These disks were the workshops where planets would later take shape, their materials gathered and sorted by gravity's patient hand. Gravity's influence extended beyond individual stars to the larger structures of galaxies. In the early universe, those initial density fluctuations grew into vast webs of matter, like a cosmic tapestry stretched across space. Scientists call this the cosmic web, a network of filaments, walls and voids where the densest regions became the birthplaces of galaxies. Imagine threads of light and matter crisscrossing the darkness, with galaxies forming at the intersections like dewdrops on a spider's web. Gravity pulled these threads together, shaping irregular clumps into the spirals, ellipticals and irregular galaxies we see today. This cosmic web wasn't just a backdrop. It was a dynamic system alive with motion. Galaxies collided and merged, their stars and gas mingling under gravity's guidance, like rivers joining to form a mightier stream. These mergers sculpted galaxies into their familiar shapes, with spiral arms curling like ribbons or elliptical galaxies glowing like soft rounded lanterns. Gravity was the artist, blending and reshaping, ensuring that no two galaxies were quite the same, yet all were bound by its universal rule. Let's not forget the planets, those smaller, more intimate creations. Within the disks around young stars, gravity continued its work, pulling dust grains together, one tiny collision at a time. These grains stuck, forming pebbles, then boulders, then planetesimals, the building blocks of planets. It's a process so delicate it's almost like the universe is knitting stitch by stitch, creating worlds from the simplest ingredients. Gravity ensured that these growing clumps stayed together, orbiting their stars, gathering more material until they became the rocky worlds or gas giants we know today. This gentle pull of gravity is something we experience every day, keeping our feet on the ground, holding our coffee in its cup. But in the cosmos, it's a force of creation, not just of holding things in place. It's the reason the moon orbits Earth, the reason our solar system spins in harmony, the reason galaxies cluster together in the vastness of space. It's like a cosmic glue binding the universe's pieces into a coherent whole, from the smallest dust grain to the largest galaxy cluster. The beauty of gravity lies in its simplicity. It doesn't need complex rules or flashy displays. It's a force that works the same whether it's pulling a leaf to the ground or a galaxy into being. Yet its effects are profound, shaping the universe over billions of years, turning the chaos of the Big Bang into the ordered structures we see today. It's a reminder that creation doesn't always need to be loud or sudden. Sometimes the most magnificent things are built slowly, quietly, with a gentle nudge that never gives up. As we drift through this story, let's hold on to the image of gravity as a cosmic gardener, tending to the universe's nurseries, coaxing clouds into stars, stars into galaxies, and dust into planets. You're part of this process too, made of atoms shaped by gravity's touch, living on a world it helped create. The same force that holds you to Earth once gathered the materials for its birth billions of years ago in a universe still learning to weave its dreams. Rest easy knowing that gravity is still at work, pulling, shaping, creating as the cosmos spins its endless tale. As gravity worked its quiet magic, pulling molecular clouds into denser clumps across the young universe, something extraordinary began to emerge. Picture a dark, vast canvas still cooling from the Big Bang's glow, now speckled with faint glimmers of light like fireflies waking in a twilight field. These were the first galaxies, fragile and small, nothing like the grand spirals or glowing ellipticals we know today. They were irregular, chaotic clusters of stars born in the densest pockets of the cosmic web where gravity had woven its earliest threads. These infant galaxies, often called dwarf galaxies, were the universe's first experiments in creation, humble beginnings that would grow into the cosmic cities we see in the night sky. Their birth marks a turning point when the universe began to shine, setting the stage for stars and planets to follow. Let's imagine the universe a few 100 million years after the Big Bang, still a young place barely 1 billion years old. The cosmic microwave background, that faint glow from the universe's infancy, still bathed everything in a soft light, but the darkness was giving way. In the densest regions of the cosmic web, where gravity had gathered vast clouds of hydrogen and helium, the first stars were igniting. These weren't solitary stars born alone in quiet corners. They formed in clusters, dozens or hundreds at a time, their light blending together like a chorus of candles in the dark. These clusters were the hearts of the first galaxies, small and irregular, like sketches the universe was still refining. These early galaxies were tiny by today's standards, often called dwarf galaxies, containing just a few million stars compared to the hundreds of billions in our Milky Way. They were messy, lacking the elegant spirals or smooth shapes of later galaxies, more like scattered handfuls of stardust than organized structures. Yet they were vibrant, filled with massive hot stars that burned brightly and died quickly, exploding as supernovae. These explosions scattered heavier elements, carbon, oxygen, nitrogen, into the surrounding gas, enriching it for future generations of stars and planets. It's as if these first galaxies were cosmic gardeners sowing seeds for the universe's next chapters. The stars in these galaxies were different from our Sun. They were giants, hundreds of times more massive, born from nearly pure hydrogen and helium, with almost no heavier elements. Scientists call them Population 3 stars, the first generation formed when the universe was still pristine. Their light was intense, their lives short, lasting only a few million years before collapsing in spectacular bursts. These explosions not only enriched the gas around them, but also sent shockwaves through the clouds, triggering new collapses, sparking more stars. It's like a cosmic chain reaction, where each star's death fueled the birth of others, weaving the galaxy tighter with every cycle. How do we know about these first galaxies so distant in time and space? Our telescopes, like time machines, peer into the past, capturing light that left these galaxies billions of years ago. The Hubble Space Telescope and the James Webb Space Telescope have glimpsed these faint ancient objects, their light stretched by the universe's expansion into the red end of the spectrum, a phenomenon called redshift. These observations show us galaxies as they were when the universe was young, small and irregular, glowing faintly against the cosmic dark. It's like looking at a photograph of the universe as a toddler, full of potential, but still finding its shape. These early galaxies didn't form in isolation. They were part of the cosmic web, that vast network of filaments and walls where matter clustered under gravity's pull. In the densest intersections, multiple star clusters merged, drawn together like friends gathering around a campfire. Over millions of years, these mergers built larger galaxies, some growing into the ancestors of the Milky Way. The process was slow, like dough, rising in a warm kitchen, but relentless, as gravity pulled more matter into the fold, creating structures that spanned tens of thousands of light years. The birth of these galaxies wasn't just a scientific event. It was a transformation of the cosmos itself. Before them, the universe was a dark, quiet place lit only by the fading glow of the Big Bang. These first galaxies brought light, structure and complexity like the first notes of a symphony that would grow richer with time. They were the universe's first attempt at organization, its first step toward creating the vast, interconnected tapestry we see today. And within these galaxies, the seeds of planets were already taking shape as the dust from dying stars began to gather in the disks around their successors. This story of creation feels distant, yet it's deeply personal. The elements forged in those early stars, carbon, oxygen, iron, are the same ones that make up your body, your breath, the ground beneath your feet. The first galaxies were the crucibles where these elements were born, scattered by supernovae to become part of new stars, new planets, new lives. It's a humbling thought, isn't it? That the light from those ancient galaxies still travelling across the cosmos connects you to the universe's earliest moments as you listen to this story under a starry sky. The birth of these galaxies also reminds us of the universe's patience. It didn't rush to create the Milky Way or Earth. It took its time, letting gravity gather, stars ignite, and galaxies merge over hundreds of millions of years. It's a process that feels almost serene, like a river carving a valley steady and unhurried. Yet from this slow work came the vast structures that light up the night sky, the homes of countless stars and worlds, each one a testament to the universe's creative power. As we drift through this cosmic tale, let's hold on to the image of those first galaxies, small and chaotic, yet brimming with light. They were the universe's first steps toward becoming what it is today, a place of endless wonder where stars are born, planets form, and life can dream. You're part of this story, a spark of stardust from those early days resting now in the quiet of night, carried by the same forces that shaped the cosmos. Let this thought soothe you as we journey deeper into the birth of galaxies and planets, one gentle moment at a time. With the first galaxies twinkling like scattered fireflies in the young universe, the cosmos began to find its rhythm. Those early irregular clumps of stars born in the dense knots of the cosmic web were just the beginning, like rough sketches on a vast canvas. Over billions of years, these fledgling galaxies would transform, sculpted by gravity collisions and the gentle churn of cosmic forces, into the majestic shapes we see today. Spirals swirling like cosmic pinwheels, ellipticals glowing like soft lanterns, and irregulars dancing to their own chaotic beat. Imagine the universe as an artist, refining its work, blending light and matter into forms that tell stories of creation, conflict, and beauty. This is the story of how galaxies take shape, a slow, graceful process that turns the universe's first sparks into the glowing cities of the night sky. Let's picture those early galaxies, small and disorderly, filled with massive stars that burned bright and died young. These dwarf galaxies, with their handfuls of stars, were like villages in the cosmic wilderness scattered across the expanding universe. They didn't stay isolated for long. Gravity, ever the matchmaker, pulled them toward one another like friends drawn together at a quiet gathering. When galaxies met, they didn't just pass by, they merged their stars and gas, mingling in a cosmic dance that could last millions of years. These mergers were the crucible where galaxies grew, transforming from small chaotic clusters into larger, more structured forms. The process of galaxy mergers is like a slow-motion waltz across the cosmos. Imagine two galaxies, each with its own stars, gas and dust, spiraling toward one another. As they draw closer, gravity stretches them, pulling out long tails of stars like ribbons trailing in a breeze. Their gas clouds collide, sparking bursts of star formation, lighting up the merging pair like fireworks in a silent sky. Over time, the two become one, their stars settling into new orbits, their gas pooling into new clouds ready to birth more stars. This is how galaxies grow, not just by gathering more matter, but by joining with others, blending their histories into something greater. These mergers gave rise to the diverse shapes we see today. Spiral galaxies like our Milky Way form when a galaxy's gas settles into a spinning disk, with arms curling like ripples in a pond. These arms are alive with star formation, glowing with the light of young hot stars, while older stars settle into a central bulge like a cozy village surrounded by vibrant fields. Elliptical galaxies, on the other hand, are smoother rounded like glowing orbs in the sky. They often form when multiple galaxies merge their stars, scattering into a more uniform shape like dough kneaded into a single loaf. Irregular galaxies, those that resist tidy forms, keep their chaotic charm, shaped by violent mergers or bursts of star formation that disrupt their structure. The Milky Way itself is a product of this cosmic sculpting. Billions of years ago, it began as a small irregular galaxy, one of many in the early universe. Over time, it merged with others, growing larger, its stars and gas settling into the spiral arms we see today. Even now, it's not finished. It's on a collision course with the Andromeda Galaxy, our nearest neighbour, in a merger that will unfold over billions of years, creating a new, larger galaxy. It's a reminder that galaxies are not static. They're alive, evolving, shaped by the universe's endless creativity. This shaping process wasn't just about gravity's pull. Other forces played a role, like the spin of galaxies inherited from the turbulence of their parent clouds. As galaxies formed, they spun their angular momentum, shaping their disks and arms, like a potter's wheel guiding clay into a bowl. Magnetic fields threaded through the gas, influencing how stars formed, while supernovae from dying stars sent shockwaves compressing gas and sparking new births. It's as if the universe was a symphony, with gravity conducting and stars, gas and dust playing their parts in harmony. These early galaxies were also shaped by their environment. In dense regions of the cosmic web where many galaxies clustered, mergers were frequent, creating massive ellipticals. In quieter regions, galaxies could grow more slowly, forming delicate spirals. The universe's structure, that web of filaments and voids, acted like a cosmic blueprint guiding where and how galaxies took shape. It's a beautiful thought, isn't it? That the universe's architecture laid down in the Big Bang still influences the forms of galaxies billions of years later. The birth and shaping of galaxies also set the stage for planets. Within these galaxies, stars formed in clusters, each surrounded by disks of gas and dust, the raw materials for planets. As galaxies grew and merged, they created richer environments, with more elements forged by dying stars ready to form rocky worlds and gas giants. The galaxies became the homes where planetary systems could thrive like neighborhoods, where families of stars and planets could settle. This story of galactic evolution has been pieced together by astronomers who study the light from distant galaxies to learn their histories. Telescopes like the James Webb Space Telescope capture images of galaxies as they were billions of years ago, showing us their chaotic youth. These observations reveal a universe in constant motion, where galaxies are not just born but reborn, reshaped by mergers and star formation, like a painting that's never quite finished. As we drift through this cosmic tale, let's hold on to the image of galaxies taking shape, their stars and gas swirling into forms that light up the night sky. They're more than just collections of stars, they're stories of creation, of collisions and connections, of chaos giving way to beauty. You're part of this story too, living in a galaxy shaped by billions of years of cosmic artistry, your atoms forged in the same stars that lit the universe's youth. Rest easy, knowing that the galaxies are still spinning, still merging, still crafting their shapes in the endless dance of the cosmos. As galaxies began to take shape, swirling into spirals and glowing as ellipticals, their hearts came alive with the birth of stars. Picture a galaxy as a vast glittering city, its streets lined with countless points of light, each one a star burning brightly in the cosmic night. These stars are more than just beacons. They are the universe's forges, where the simplest elements, hydrogen and helium, are transformed into the building blocks of planets and life. Inside their fiery cores, stars weave carbon, oxygen and iron, scattering these treasures across the cosmos when they die. It's a gentle, relentless process, like a blacksmith shaping metal, turning the raw materials of the Big Bang into the stuff of worlds. This is the story of how stars become the creators of everything we know, forging the elements that make planets possible. Let's drift into one of those stellar nurseries we visited earlier, a molecular cloud within a young galaxy swirling with gas and dust. Deep within, gravity has pulled a dense core together like a knot tightening in a rope. This core, a protostar, grows hotter as it collapses, its particles colliding and heating up, like embers glowing brighter in a campfire. When the temperature reaches millions of degrees, something miraculous happens. Nuclear fusion ignites, hydrogen atoms smash together, fusing into helium, releasing energy that pushes back against gravity's pull. The protostar becomes a true star, shining steadily a new light in the galaxy's tapestry. These stars, especially the massive ones born in the universe's early days, were the first cosmic forges. Unlike our sun, which burns slowly over billions of years, these early giants were hot and hungry, racing through their fuel in mere millions of years. Inside their cores, the pressure and heat were so intense that they didn't stop at helium. They fused helium into carbon-carbon into oxygen, and oxygen into heavier elements like neon, magnesium and silicon. Each step up the periodic table was like climbing a ladder, building more complex materials with every fusion reaction, like a chef adding new ingredients to a cosmic stew. The most massive stars went even further, forging elements all the way up to iron. But iron is where the forging stops. Unlike lighter elements, fusing iron doesn't release energy. It consumes it like trying to light a fire with wet wood. When a star's core fills with iron, its fusion engine stalls and gravity takes over, collapsing the star in a spectacular supernova. These explosions are among the universe's grandest events, outshining entire galaxies for a brief moment, scattering their forged elements, carbon, oxygen, iron, and more into the surrounding space. It's as if the star in its final act gifts its creations to the cosmos, like a painter flinging colours across a canvas. These scattered elements are the seeds of planets. The carbon and oxygen mix with the hydrogen and helium in molecular clouds, enriching them for the next generation of stars. When these newer stars form, they're surrounded by disks of gas and dust, now laced with heavier elements. These disks are where planets are born as dust grains stick together to form rocks, then boulders, then worlds. Without the work of those early stars, there would be no rocky planets like Earth, no oceans, no mountains, no life. Every atom of carbon in your body, every speck of iron in your blood was forged in the heart of a star that lived and died billions of years ago. Let's linger on this idea for a moment. The stars aren't just distant lights. They're the alchemists of the universe, turning the simple into the complex. Our Sun, a modest star by cosmic standards, is part of this lineage, born from a cloud enriched by earlier supernova. Its planets, including Earth, are built from the ashes of those ancient stars, their elements gathered by gravity into the world we call home. It's like a cosmic family tree connecting you to stars that shone long before the sun was born, their light now faded, but their legacy enduring in every breath you take. This process of stellar forging wasn't a one-time event. It's ongoing, happening in galaxies across the universe. In the Orion Nebula, a stellar nursery visible from Earth, new stars are igniting forging elements as we speak. Their supernovae will enrich the galaxy, further ensuring that future stars and planets have even more materials to work with. It's a cycle of creation where each star's death fuels new births, like a forest regrowing after a fire, each generation stronger and more diverse than the last. Astronomers have pieced together this story by studying the light from stars and the remnants of their explosions. Spectroscopy. The art of breaking light into its colours reveals the elements within stars, showing us the carbon, oxygen and iron they produce. When we look at supernovae, we see these elements scattered across space, their spectral fingerprints glowing in the debris. It's like reading a star's diary, each line revealing what it created in its lifetime, what it left behind for the universe to use. This forging process also shaped galaxies themselves. As stars formed and died, their supernovae sent shockwaves through the gas, triggering new star formation, helping galaxies grow denser and more structured. The elements they scattered enriched the galactic environment, making it possible for more complex systems, stars with planets with life to emerge. It's a beautiful thought, isn't it? That the stars, in their fiery lives and explosive deaths, are the universe's builders, creating the materials that make galaxies vibrant and planets possible. As we drift through this cosmic tale, let's hold on to the image of stars as forges their cores, glowing with the power to create. They're not just lights in the sky. They're the makers of worlds, the weavers of elements, the ancestors of every planet we know. You're part of this story too, a fragment of stardust forged in those ancient fires, living on a world shaped by their gifts. Rest easy, knowing that the stars are still burning, still forging, still scattering their treasures across the cosmos as the universe continues its endless work of creation. As stars ignite within the glowing nurseries of galaxies, their light casts a gentle glow on the next chapter of cosmic creation. Picture a young star, newly born, surrounded by a swirling veil of gas and dust, spinning like a dancer's skirt caught in a soft breeze. This is the protoplanetary disk, a cosmic workshop where the raw materials of planets gather, twirl, and slowly come together. These disks are the cradles of worlds where tiny grains of dust begin a delicate dance that transforms them into rocky planets, gas giants, and everything in between. It's a process as graceful as it is profound, like a symphony played in silence across millions of years, turning the scattered remnants of star formation into the ordered orbits of planetary systems. This is the story of how planets begin to take shape, one gentle spin at a time. Let's drift closer to one of these young stars, its light still unsteady, like a candle flickering in a drafty room. As it forms, the star doesn't consume all the material in its parent cloud. Leftover gas and dust, enriched with elements like carbon and silicon from earlier supernovae, settle into a flattened disk around the star, held in place by gravity and spinning with the star's rotation. This protoplanetary disk is like a cosmic record spinning smoothly, its grooves filled with the potential for worlds. It stretches across millions of miles wider than the orbit of Neptune, yet it's thin like a sheet of paper stretched across a football field. Within this disk, the dance of planet formation begins. The gas, mostly hydrogen and helium, swirls alongside tiny dust grains, no larger than grains of sand or flakes of snow. These grains are the building blocks of planets made of silicates, carbon compounds, and ices forged in the hearts of ancient stars. As the disk spins, these grains collide, sticking together like snowflakes, forming a snowball growing into pebbles, then boulders over thousands of years. It's a slow, patient process, like a child building a sandcastle one grain at a time, each collision adding a little more to the growing clump. This clumping process, called accretion, is driven by gravity and the gentle nudge of collisions. The disk isn't a calm, orderly place, it's alive with motion, with eddies and swirls like cream stirring into coffee. These motions help dust grains find each other, their sticky surfaces bonding in the cold outer regions of the disk or melting together closer to the star's warmth. Over time, these clumps grow into planetesimals, objects the size of asteroids or small moons ranging from a few miles to hundreds of miles across. These are the seeds of planets, the first solid steps toward worlds like Earth or Jupiter. The protoplanetary disk is divided into regions, each shaping the kind of planets that form. Close to the star, where temperatures are high, only materials like metals and silicates can remain solid, forming rocky planets like Earth or Mars. These inner regions are like a cosmic forge where heat shapes sturdy, dense worlds. Farther out beyond what astronomers call the frost line, it's cold enough for ice's water, ammonia, methane to solidify. Here planetesimals can grow larger, gathering vast amounts of gas to become gas giants like Jupiter or Saturn, their massive forms dominating the outer disk like giants in a quiet village. The disk's dynamics are shaped by more than just gravity. The star's light and heat push lighter particles outward, while magnetic fields twist through the gas, guiding its flow like invisible threads. Sometimes turbulence stirs the disk, creating dense patches where planetesimals form faster like knots in a rope. Other times, the star's radiation clears gaps in the disk-carving paths, where young planets begin to orbit like trails through a cosmic forest. It's a delicate balance where every swirl, every collision contributes to the creation of a planetary system. This process isn't unique to our solar system. Astronomers have observed protoplanetary disks around countless young stars, their shapes revealed by telescopes like ALMA, the Atacama Large Millimeter Array. These disks appear as glowing rings with gaps and spirals, hinting at planets already taking shape, like ripples in a pond showing where a stone has fallen. The star HL Tauri, just 1 million years old, has a disk with clear rings, suggesting planets forming in real time, a snapshot of creation frozen in light that travelled thousands of years to reach us. The beauty of protoplanetary disks lies in their universality. Across galaxies, wherever stars are born, these disks form each one a potential nursery for planets. Some disks birth systems like ours with rocky worlds and gas giants. Others create exotic worlds, super-Earths, mini-Neptunes, or planets orbiting twin stars like something out of a science fiction tale. It's as if the universe is experimenting, trying different recipes, crafting worlds as diverse as the galaxies that host them. This dance of disks connects us to the cosmos in a personal way. The Earth you stand on began in a disk like this, orbiting a young sun, its dust grains slowly gathering into the rocks and oceans we know today. Every mountain, every river, every breath you take traces back to those swirling clouds of gas and dust spinning in the quiet of space. It's a humbling thought, isn't it? That the worlds we call home were born in the gentle whirl of a cosmic disk, billions of years ago, in a galaxy still finding its shape. As we drift through this tale, let's hold on to the image of protoplanetary disks spinning gracefully around their stars, weaving planets from the simplest grains. They're the universe's workshops, where chaos becomes order, where dust becomes worlds, and where the cosmos dreams of life. You're part of this story too, a fragment of stardust shaped by the same forces living on a planet, born in a disk's embrace. Rest easy, knowing that the universe is still spinning its disk, still crafting its world, still dancing its endless dance of creation. Within the swirling protoplanetary disks around young stars, a quiet miracle unfolds, one so delicate, it's like the universe is holding its breath. Picture a disk of gas and dust spinning gently around a newborn star, its surface shimmering with countless tiny grains no larger than specks of sand. These grains forged in the hearts of ancient stars are the seeds of planets destined to grow from humble dust into the rocky worlds we call home. Through a slow, graceful process of collisions and clumping, these particles transform, gathering into planetesimals, and eventually planets like snowflakes building into a snowball rolling across a cosmic field. This is the story of how dust becomes worlds, a tale of patience and persistence, weaving the simplest ingredients into the complex beauty of rocky planets. Let's drift into the heart of a protoplanetary disk where the star's light casts a warm glow on a sea of gas and dust. The disk is a busy place, alive with motion, like a river flowing in slow motion. The dust grains made of silicates, carbon and ices float alongside the hydrogen and helium gas carried by the disk's gentle spin. These grains are tiny, smaller than the particles in a puff of smoke, yet they hold the potential for entire worlds. As the disk orbits the star, the grains collide their surfaces sticky from ice or static charge like lint clinging to a sweater, allowing them to bond and grow. This process, called accretion, is the first step in planet formation. The collisions are soft at first, happening at speeds slower than a bicycle's roll, but they're relentless, occurring over thousands of years. The grains grow into pebbles, then into boulders, each new size making them more likely to attract others, like a snowball gathering more snow as it rolls. Gravity begins to play a role even at these small scales, pulling larger clumps together, creating objects called planetesimals, rocky or icy bodies, ranging from a few miles to hundreds of miles across like asteroids or comets in our own solar system. These planetesimals are the building blocks of rocky planets, the universe's first attempt at crafting solid worlds. In the inner regions of the disk, close to the star where temperatures are high, only materials like metals and silicates can remain solid. Here, planetesimals form from these heat-resistant ingredients growing into the cores of planets like Earth, Mars, or Venus. It's like a cosmic kitchen, where the star's heat bakes the ingredients, shaping sturdy, rocky worlds from the toughest materials. The process is slow, taking millions of years as planetesimals collide and merge their gravity, pulling in more debris like a magnet gathering iron filings. The formation of these rocky planets is a chaotic dance, not a neat assembly line. Planetesimals don't just drift together peacefully, they crash, sometimes shattering, sometimes sticking like clay being moulded by a sculptor's hands. These collisions release heat, melting parts of the growing bodies, allowing heavier materials like iron to sink to their cores, forming the layered structures we see in planets like Earth. It's a violent process, yet it's also creative, turning a jumble of rocks into a world with mountains, valleys, and the potential for oceans. In our own solar system, we see evidence of this chaotic youth. The Moon, for example, is thought to have formed when a Mars-sized planetesimal, often called Theia, slammed into the young Earth, flinging molten debris into orbit. This debris coalesced into the Moon, companion born from a cosmic accident now drifting silently beside us. Meteorites. Those ancient rocks that fall from the sky are also relics of planetesimals, their composition revealing the silicates and metals that shaped the early solar system. It's like holding a piece of the universe's childhood, a fragment from the time when dust was becoming worlds. Astronomers study this process by observing young star systems, where protoplanetary disks are still forming planets. Telescopes like ALMA capture images of these disks showing rings and gaps, where planetesimals are clearing paths like footprints in a snowy field. These observations confirm that the process is universal, happening across galaxies wherever stars are born. Each disk is a potential nursery crafting worlds, as unique as the stars they orbit, from rocky planets like ours to strange worlds we can only imagine. This journey from dust to worlds is a testament to the universe's ingenuity. It takes the simplest ingredients, grains of dust forged in long-dead stars, and transforms them into complex systems where planets spin in harmony around their suns. It's a process that feels almost alive, as if the universe is experimenting, trying new combinations, crafting worlds with care. The Earth we walk on, with its forests, rivers and skies, began as these tiny grains colliding in a disk billions of years ago in a galaxy still finding its shape. The story of rocky planet formation also connects us to the cosmos in a profound way. The elements in your body, carbon, calcium, phosphorus, were once dust grains in a protoplanetary disk, gathered by gravity, shaped by collisions, and baked into the planet you call home. You're a direct descendant of this process, a piece of stardust that found its way into a world listening now to the universe's quiet lullaby. It's a humbling thought, isn't it? That the worlds we inhabit, the lives we lead, began as specks of dust dancing in the light of a young star. As we drift through this cosmic tale, let's hold on to the image of those dust grains swirling in a protoplanetary disk, slowly building into worlds. They're the universe's smallest artists crafting planets, from the humblest beginnings, turning chaos into order and potential into reality. You're part of this story too, a spark of stardust shaped by the same gentle collisions, living on a world born from dust. Rest easy, knowing that the universe is still gathering its grains, still weaving its worlds, still dreaming its endless dreams of creation. As protoplanetary disks spin around their young stars, crafting rocky planets from dust and metal, another kind of world takes shape in the colder outer reaches. Picture a vast swirling disk, stretching far beyond the star's warm glow, where icy grains and gas gather like frost on a winter window. Here in these frigid realms, gas giants are born massive planets, like Jupiter and Saturn, cloaked in thick atmospheres, dominating their orbits like cosmic titans. These worlds, along with the moons, asteroids and comets that form from the disk's leftovers, complete the tapestry of a planetary system, turning a star's surroundings into a bustling neighbourhood. It's a story of abundance and variety where the universe uses every scrap of material, weaving grand planets and smaller remnants into a harmonious whole. Let's drift to the outer edges of a protoplanetary disk where the star's light is faint and temperatures dip low enough for ice's water, ammonia, methane to solidify. In this chilly environment, planetesimals, those rocky and icy building blocks, grow larger than their inner disk cousins. The abundance of solid material like ice-covered grains allows them to accrete quickly, gathering mass like snowballs rolling through a blizzard. These growing cores become the seeds of gas giants massive enough to pull in vast amounts of hydrogen and helium from the surrounding disk, like a sponge soaking up water from a stream. The formation of a gas giant is a dramatic process. Once a planetesimal reaches a critical mass about 10 times that of Earth, its gravity becomes strong enough to attract gas directly from the disk. This gas, mostly hydrogen and helium left over from the Big Bang, flows onto the core, building a thick atmosphere that dwarfs the rocky planets closer to the star. Jupiter, for example, likely started as a rocky core perhaps the size of a small planet, before it began gulping gas, growing into the behemoth we see today with a diameter 11 times that of Earth. It's like a cosmic vacuum cleaner sweeping up material to become a giant in the sky. Saturn, with its stunning rings, followed a similar path, its core gathering ice and gas until it became a gas giant, its rings a remnant of the disk's debris that never formed a moon. These rings are like a cosmic keepsake, a reminder of the disk's chaotic youth sparkling in the starlight. Gas giants like these dominate their systems, their gravity shaping the orbits of other planets and debris, like conductors leading an orchestra of celestial bodies. Their presence ensures that the disk's material is used efficiently, leaving little to waste. But not all material in the disk becomes planets. The leftovers, dust rocks and ices that don't coalesce into larger bodies, form a variety of smaller objects. Moons are one such creation, often forming in miniature disks around gas giants, like echoes of the larger protoplanetary disk. Jupiter's moon, Ganymede, larger than Mercury, likely formed from material orbiting the young Jupiter, accreting in a subdisk as the giant planet grew. These moons are like children of the gas giants born from the same processes, orbiting their parents in quiet harmony. Asteroids and comets are the disk's other leftovers, scattered across the system like crumbs on a cosmic tablecloth. Asteroids mostly rocky form in the inner disk, where temperatures are too high for ices like the asteroid belt between Mars and Jupiter in our solar system. Comets, with their icy cores and spectacular tails, originate in the outer disk where cold preserves their volatile materials. These objects are relics of the planet-forming process planetesimals that never grew large enough to become planets drifting in orbits that can last billions of years. The formation of gas giants and these leftovers is a testament to the universe's efficiency. Nothing goes to waste, every grain, every molecule finds a role, whether as a massive planet, a moon, or a wandering comet. In our solar system, we see this diversity in action: Jupiter and Saturn, with their thick atmospheres and retinues of moons, the asteroid belt a graveyard of planetesimals, and comets like Halley's, which swing by Earth every few decades, their tails glowing with released gases as they near the sun. It's like a cosmic scrapbook preserving the story of our system's birth. Astronomers study these processes by observing young star systems, where protoplanetary disks are still active. Telescopes like the Atacama Large Millimeter Array reveal disks with gaps carved by forming gas giants, their gravity sweeping clear paths like a broom through dust. These observations show us that gas giants form quickly within a few million years before the disk's gas dissipates, while smaller leftovers like asteroids and comets can linger longer, some surviving to the present day. It's a snapshot of creation captured in light that travelled thousands of years to reach us. This process connects us to the cosmos in a tangible way. The earth you walk on, the air you breathe, even the water in your glass, all trace back to the materials in a protoplanetary disk. The gas giants, with their massive presence, helped shape our solar system, guiding smaller bodies into stable orbits, protecting Earth from excessive impacts. The asteroids and comets, those cosmic leftovers, sometimes fall to Earth, bringing clues about our origins like letters from a distant past. You're part of this story, a fragment of stardust that found its place in a system shaped by these grand and humble creations. The formation of gas giants and their leftovers is a reminder of the universe's creativity. It takes the same disk that crafts rocky worlds and spins it into giants' moons and wandering rocks, each with its own role in the cosmic dance. It's a process that feels almost poetic, as if the universe is weaving a tapestry using every thread to create something beautiful. As we drift through this tale, let's hold on to the image of those swirling discs crafting worlds, from gas and dust building giants and scattering crumbs across the cosmos. Rest easy, knowing that the universe is still spinning its discs, still crafting its giants, still dreaming its endless dreams of creation. As we drift through the story of how galaxies and planets are born, let's turn our gaze to the humans who first looked up and wondered about the cosmos. Long before telescopes and equations, before we knew of protoplanetary disks or the Big Bang, ancient cultures saw the night sky as a tapestry of stories woven with gods, heroes, and dreams. To them, the stars and planets weren't just distant lights. They were signs, guides, and mysteries, sparking tales that shaped their understanding of creation. From the Mesopotamian plains to the Andean highlands, these early observers crafted myths about the birth of the heavens, their imaginations as boundless as the universe itself. This is the story of how ancient eyes saw the sky, connecting us to the cosmic dance of galaxies and planets through the lens of human wonder. Imagine standing on a quiet hillside thousands of years ago, the sky above a glittering sea of stars unmarred by city lights. To the ancient Babylonians living in what is now Iraq around 2000 BCE, the stars were the work of Marduk, their creator god, who shaped the heavens after a cosmic battle. They saw the Milky Way, our galaxy, as a celestial river, its milky glow a path for divine beings. Planets which wandered against the fixed stars were messengers of the gods, their movements tracked with meticulous care. These early astronomers recorded the motions of Venus and Jupiter on clay tablets, not knowing they were planets born in a protoplanetary disk, but sensing their importance in the cosmic order. Across the world, the ancient Egyptians saw the sky as the body of Nut, the goddess of the heavens, her star-strewn form arching over the earth. They believed the sun and planets were born from her, travelling across her body each night, a story echoing the real cosmic births we now study. In ancient China, astronomers like those of the Han Dynasty charted the stars, naming constellations and tracking planets, which they called wandering stars. They saw the cosmos as a harmonious system, its cycles reflecting the balance of life on Earth, a poetic parallel to the ordered orbits of planets around their stars. In the Americas, the Maya built observatories like the one at Chichen Itza to watch the sky with astonishing precision. They tracked Venus's cycles, linking them to myths of creation and rebirth, as if the planet's movements mirrored the universe's own birth from chaos. Their calendars, carved in stone, aligned with cosmic events, showing a deep understanding of the sky's rhythms, even without knowing the science of galaxy formation. The Aboriginal peoples of Australia told of the Dreamtime, a timeless era when ancestral beings shaped the land and sky, their stories painting the Milky Way as a river of spirits, a reflection of the galaxy's star-filled arms. These ancient perspectives weren't just myths. They were attempts to make sense of the cosmos, to find meaning in the lights above. The Greeks, for instance, saw planets as divine wanderers, naming them after gods like Hermes and Aphrodite, Mercury and Venus to us. Philosophers like Aristotle speculated about the heavens, imagining Earth at the centre of a universe filled with crystalline spheres, each carrying a planet or star. While their science was wrong, their curiosity was right, laying the groundwork for later astronomers who would unravel the true nature of galaxies and planets. Fast forward to the Renaissance, and figures like Nicholas Copernicus shifted our view. Copernicus proposed that the Sun, not Earth, was the centre of the solar system, a revolutionary idea that placed planets in orbits around a star, hinting at their formation in a disk. Galileo Galilei, with his telescope, observed Jupiter's moons, proving that not everything revolves around Earth, a step toward understanding planetary systems. These discoveries, built on ancient observations, brought us closer to the truth. Planets and stars are part of galaxies born from cosmic processes stretching back to the Big Bang. Even today, the stories we tell about the cosmos echo those ancient myths. In science fiction, like Star Wars, galaxies are vast playgrounds filled with planets teeming with life, a modern take on the idea of a cosmos alive with meaning. The Voyager spacecraft, launched in 1977, carried a golden record with pulsar signals to mark Earth's place in the galaxy, a nod to ancient navigators who used stars to guide their way. It's as if we're still telling the same stories, but with new tools, telescopes instead of myths, equations instead of gods. These cultural perspectives connect us to the cosmos in a profound way. When you look at the night sky, you're sharing a moment with ancient stargazers who wondered just as you do about the origins of the stars and planets, the Milky Way. A faint band of light to them is now known to be our galaxy born from mergers and star formation, yet it remains a source of wonder. The planets once divine wanderers are now worlds we study, their births traced to protoplanetary disks, yet they still inspire awe. This blend of ancient curiosity and modern science reminds us that the story of galaxies and planets is not just a tale of physics, it's a human story. The elements in your body forged in stars were seen by ancient eyes as divine sparks. The planets you dream of orbiting distant suns were once gods to those who watch the sky. You're part of this tradition, a stargazer in your own right, listening to the universe's lullaby as you drift towards sleep. As we journey through this cosmic tale, let's hold on to the image of those ancient skies filled with stories of creation. They remind us that galaxies and planets are more than matter. They're symbols of wonder, connecting us across time to the first humans who looked up and dreamed. Rest easy knowing that the cosmos is still telling its stories, still inspiring myths, still weaving its stars and worlds in the quiet of the night. You're part of this endless narrative, a spark of curiosity born under the same ancient sky. As we journey through the cosmic tale of how galaxies and planets are born, let's imagine turning our gaze upward, not with the naked eye, but through the lenses of humanity's greatest tools. Picture a telescope, its mirror gleaming like a quiet pond, capturing light that began its journey billions of years ago when the universe was young. Telescopes like Hubble and the James Webb Space Telescope are our windows into the past, letting us witness the birth of galaxies and the formation of planets as they happened eons ago. They transform the night sky into a cosmic archive where every photon tells a story of creation, from the first irregular galaxies to the swirling disks where worlds take shape. This is the story of how we peer through time, uncovering the universe's infancy, with each faint glimmer of light. Let's begin with the Hubble Space Telescope, launched in 1990, a marvel of human ingenuity orbiting high above Earth's atmosphere. Imagine it as a silent sentinel, its mirror gathering light from the farthest reaches of space, where galaxies glow as they did when the universe was just a fraction of its current age. Hubble's deep space images, like the famous Hubble Deep Field, reveal thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. These galaxies, some seen as they were just 1 billion years after the Big Bang, are small, irregular and chaotic, like cosmic toddlers still learning to walk. Their light, stretched by the universe's expansion, arrives, red-shifted a clue to their ancient origins, like a letter mailed long ago finally reaching its destination. Hubble's observations have shown us the universe's youth, a time when galaxies were forming in the dense knots of the cosmic web, their stars igniting in bursts of creation. These images capture the mergers that shaped early galaxies, their collisions sparking new stars like fireworks in a silent sky. Hubble also glimpses protoplanetary disks around young stars, their dusty rings hinting at planets in the making like shadows of worlds yet to be born. It's as if Hubble is a cosmic historian piecing together the story of how galaxies and planets came to be each snapshot a page in the universe's grand book. Now let's drift to the James Webb Space Telescope, launched in 2021, a newer, more powerful eye on the cosmos. Imagine Webb as a gentle giant, its golden mirror larger than Hubble's, designed to capture infrared light, the glow of objects too cool or distant for visible light. Infrared lets Webb peer through cosmic dust like seeing through fog, revealing the hidden nurseries where stars and planets form. It also allows us to see even farther back to galaxies that existed just a few 100 million years after the Big Bang, when the universe was a mere infant. These galaxies, faint and irregular, are the ancestors of our Milky Way, their light travelling for over 13 billion years to reach us. Webb's images are like a time machine, showing us galaxies in their chaotic youth, merging and growing their stars, forging the elements that would later build planets. One of Webb's early discoveries was galaxies brighter and larger than expected at such early times, suggesting that galaxy formation began sooner and faster than we thought, like a garden blooming before spring. Webb also captures detailed views of protoplanetary disks, their rings and gaps carved by forming planets, offering clues about how worlds like Earth take shape. It's as if Webb is a cosmic detective, uncovering secrets hidden in the universe's earliest chapters. These telescopes don't just show us distant objects, they let us travel through time. Light takes years, centuries, or billions of years to reach us, so when we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago, not as it is today. This cosmic delay turns every telescope into a portal, letting us witness the universe's history unfold from the birth of the first galaxies to the formation of planetary systems. It's like flipping through an ancient photo album, each image capturing a moment in the cosmos's long journey. Beyond Hubble and Webb, other telescopes contribute to this story. The Atacama Large Millimeter Array, or ALMA, observes young star systems in our galaxy, its radio waves revealing protoplanetary disks in exquisite detail, like brushstrokes on a canvas. ALMA shows us planets forming in real time, their gravity sculpting rings and spirals in the dust, a process that mirrors the birth of our own solar system. Ground-based telescopes like those at Mauna Kea study the spectra of distant galaxies, revealing their composition and motion, like reading the fingerprints of creation. This scientific quest connects us to the ancient stargazers who looked up with wonder, though they had only their eyes and myths. Today we use mirrors and mathematics, but the curiosity is the same, driving us to ask how galaxies and planets are born. These telescopes are our modern campfires around which we gather to tell stories of the cosmos, each discovery a new tale of creation. The light they capture is a bridge between past and present, linking us to the universe's youth, when the first stars lit the dark and the first planets began to spin. This journey through time also reminds us of our place in the cosmos. The galaxies we see in Hubble's images, the disks in Webb's infrared glow, are part of the same universe that shaped our world. The elements in your body, forged in ancient stars, were part of those early galaxies scattered by supernovae to become planets like Earth. You're a fragment of that cosmic history, a spark of stardust carried through billions of years, listening now to the universe's quiet lullaby as you rest. As we drift through this cosmic tale, let's hold on to the image of those telescopes, their mirrors catching light from the universe's dawn. They're our guides, showing us how galaxies and planets were born, revealing a cosmos alive with creation. Rest easy, knowing that the universe is still shining, still crafting its stories, still sending its ancient light to those who look up with wonder. You're part of this endless journey, a dreamer under the same cosmic sky, cradled by the light of stars born long ago. As we journey through the cosmic tale of how galaxies and planets are born, let's bring the story closer to home, to the familiar worlds that spin quietly around our sun. Picture our solar system, a cozy neighbourhood in the vast city of the Milky Way, where Earth, Mars, Jupiter and their siblings orbit in graceful harmony. These planets, born from the same processes that shaped distant galaxies and stars, are the result of dust and gas swirling in a protoplanetary disk billions of years ago. Their formation is a story of cosmic craftsmanship, turning scattered grains into the rocky landscapes and gaseous giants we know today. It's a tale that connects the grand sweep of the universe to the ground beneath your feet, making the birth of planets feel as intimate as a walk under the stars. Let's drift back about 4.6 billion years to a time when the Sun was a young star newly ignited in a molecular cloud within the Milky Way. Around it formed a protoplanetary disk, a spinning veil of gas and dust, rich with elements forged in ancient stars, carbon, oxygen, silicon and iron. This disk was like a cosmic workshop where the materials for our solar system gathered ready to be shaped. In its inner regions, where the sun's heat was fierce, dust grains of metal and silicates collided and stuck, forming planetesimals, the seeds of rocky planets like Earth, Venus, Mercury and Mars. It's as if the universe was baking a batch of sturdy worlds, using only the toughest ingredients that could withstand the sun's warmth. Earth's formation began with these planetesimal small rocky bodies crashing together in a chaotic dance. Over millions of years they merged, growing larger like pebbles piling into a mound. One monumental collision with a Mars-sized body called Theia reshaped Earth's early history. The impact flung molten debris into orbit, which coalesced into the Moon, a quiet companion that still lights our nights. This violent birth left Earth with a molten surface slowly cooling to form a crust like a cake setting in a cosmic oven. Over time, water vapor from the disk and comets condensed into oceans, turning our planet into a blue jewel capable of hosting life. Mars, our red neighbour, followed a similar path, its rocky surface forming from planetesimals in the inner disk. Smaller than Earth, it cooled faster, its volcanoes and canyons freezing. In time, like a snapshot of a young world's ambition, Venus, closer to the Sun, became a scorching twin to Earth, its thick atmosphere trapping heat, a reminder that a planet's fate depends on its place in the disk. Mercury's smallest and closest to the Sun is a dense ball of metal forged in the hottest part of the disk like a piece of iron left too close to the fire. Each rocky planet tells a unique story shaped by the same processes but moulded by their distance from the Sun. Beyond the frost line where the disk was cold enough for ices to form gas giants like Jupiter and Saturn took shape. These giants began as rocky cores growing massive enough to pull in vast amounts of hydrogen and helium like sponges soaking up the disk's gas. Jupiter, the largest, became a cosmic titan, its gravity shaping the orbits of other planets and capturing dozens of moons like a king gathering a court. Saturn, with its iconic rings, formed similarly, its rings a remnant of icy debris that never became a moon, sparkling like a cosmic crown in the sun's light. The outer solar system hosts the ice giants Uranus and Neptune, born in the disk's farthest reaches, where ices like methane and ammonia were abundant. These planets, smaller than their gas giant siblings, gathered less gas, but more ice. Their blue-green hues a testament to their chilly origins. Their moons and rings, like those of Jupiter and Saturn, formed from leftover material, orbiting in quiet synchrony, like dancers following a distant rhythm. The solar system's leftovers, asteroids, comets, and dwarf planets like Pluto are relics of this formation process. The asteroid belt between Mars and Jupiter is a graveyard of planetesimals that never became a planet, their orbits disrupted by Jupiter's massive gravity. Comets with their icy cores originate in the distant Kuiper belt and Oort cloud, swinging past the sun to display their glowing tails, like cosmic travelers sending postcards from their journeys. These objects are time capsules preserving the dust and ice from the solar system's birth like keepsakes from a long-ago celebration. Astronomers study our solar system to understand planet formation across the universe. Meteorites, fragments of asteroids that fall to Earth, reveal the composition of the early disk, their minerals matching those in protoplanetary disks seen around other stars. Space missions like NASA's Voyager and New Horizons have explored our planets and their moons, showing us the diversity of worlds born from a single disk. It's like reading a family album, each planet a sibling with its own personality shaped by the same cosmic story. This story of our solar system connects us to the broader cosmos. The processes that formed Earth and its neighbours are the same ones crafting planets in distant galaxies, from the swirling disks to the collisions of dust. The carbon in your body, the water in your glass, the iron in your tools, all were born in a disk like the one that created our planets billions of years ago. You're a part of this cosmic neighbourhood, living on a world shaped by the universe's patient craftsmanship under a sky filled with stars that share the same story. As we drift through this cosmic tale, let's hold on to the image of our solar system, a family of planets born from a swirling disk, each one a unique creation. They remind us that the universe's story is our story too, connecting the ground beneath your feet to the stars above. Rest easy knowing that the cosmos is still crafting its worlds, still spinning its disks, still weaving its endless tale of creation. You're a spark in this story, a fragment of stardust dreaming under the same sky that birthed your world. As we near the end of our journey through the birth of galaxies and planets, let's linger on a profound truth. The universe is a master of renewal. Picture the cosmos as a vast recycling plant where nothing is truly lost, only transformed. Stars die in brilliant supernovae, scattering their elements to form new stars and planets. Galaxies merge their gas and dust, blending to spark fresh waves of creation. Planets too evolve their surfaces, reshaped by time, ready to become the seeds of future worlds. This cycle of birth, death, and rebirth weaves through the fabric of the universe, ensuring that every ending is a new beginning, like a river flowing from one valley to the next. It's a story of cosmic resilience connecting the galaxies and planets we see today to the endless process of creation. Let's start with stars, the heart of this cosmic cycle. When a massive star reaches the end of its life, it doesn't fade quietly, it explodes as a supernova, a burst of light that can outshine an entire galaxy. Imagine a star, its core filled with iron, collapsing under gravity's weight, then rebounding in a shockwave that flings its outer layers into space. These layers carry the elements forged in the star's core: carbon, oxygen, nitrogen, and iron, spreading them across the galaxy like seeds scattered by a cosmic wind. These elements enrich molecular clouds, making them fertile for the next generation of stars and planets, like compost nourishing a garden. This enrichment is crucial for planet formation. The first stars born from pure hydrogen and helium had no rocky planets, as there were no heavier elements to form them. But their supernovae created the materials needed for worlds like Earth, with its mountains, oceans, and life. Each new generation of stars inherits this legacy, forming in clouds, laced with the ashes of their ancestors, their protoplanetary disks ready to craft planets. It's as if the universe is learning each cycle, building more complex systems from simple stars to worlds capable of hosting life. Galaxies too are part of this recycling process. They don't remain static. They evolve, merging with one another in cosmic dances that span billions of years. Picture two galaxies like the Milky Way and Andromeda spiraling toward each other, their gravity pulling stars and gas into long glowing tails. When they merge, their gas clouds collide, sparking bursts of star formation, like fireworks celebrating a new union. These mergers create larger, more complex galaxies, their structures reshaped into spirals, ellipticals, or irregular forms like clay moulded by a sculptor's hands. The gas and dust from these mergers fuel new stellar nurseries, ensuring the galaxy's legacy continues. This galactic recycling isn't just about growth, it's about transformation. Some galaxies, after exhausting their gas, become quiescent, their star formation slowing, like a forest entering a quiet season. Others in dense clusters collide frequently, their mergers triggering waves of creation that ripple through the cosmic web. Even the supermassive black holes at galaxy centers play a role, their gravity pulling in gas that heats and glows, sometimes blasting jets that stir the surrounding material like a cosmic blender, mixing ingredients for new stars. It's a dynamic process where galaxies are both creators and creations, part of an endless cycle. Planets, though smaller, are also recycled. On Earth, tectonic plates shift, grinding old crust into the mantle, while volcanoes spew new rock like a planet renewing its skin. Meteorites, remnants of the solar system's birth, fall to Earth, carrying materials that hint at our origins like letters from a distant past. In other systems, planets may be destroyed, their debris scattered into new disks ready to form second-generation worlds. It's as if the universe is a cosmic workshop, reusing every scrap to craft something new, from the smallest rock to the grandest galaxy. Astronomers observe this cycle across the universe. Telescopes like the James Webb Space Telescope capture galaxies in the act of merging their stars and gas blending to form new structures. ALMA reveals stellar nurseries enriched by supernovae, their dust glowing with the elements of dead stars. In our solar system, meteorites and comets show us the raw materials of planet formation, preserved for billions of years. These observations are like glimpses into a cosmic factory, where creation and destruction work hand in hand, each process feeding the next. This cycle connects us to the cosmos in a deeply personal way. The carbon in your body, the oxygen in your breath, the iron in your blood, all were recycled through stars that lived and died long before our sun was born. The Milky Way, our home galaxy, is itself a product of mergers, its spiral arms shaped by countless collisions. Earth, a rocky world born in a protoplanetary disk, is part of this cycle. Its surface constantly renewed its materials, tracing back to the universe's earliest moments. You're a living testament to this cosmic recycling, a spark of stardust carried through billions of years of creation. The beauty of this cycle lies in its continuity. The universe doesn't waste its materials. It reuses them, transforming endings into beginnings, like a story that never truly ends. Stars die to birth planets. Galaxies merge to form new stars, and planets evolve to host new possibilities. It's a process that feels almost alive, as if the cosmos is breathing, dreaming, and creating with every turn of its cycle. It's a reminder that nothing is lost, only changed, and that every piece of the universe has a role in its endless tale. As we drift through this cosmic story, let's hold on to the image of the universe as a recycling plant weaving new creations from the ashes of the old. It's a place where galaxies and planets are born, die, and are born again, each cycle adding to the cosmos's beauty. Rest easy knowing that you're part of this endless renewal, a fragment of stardust shaped by the universe's tireless work, dreaming under a sky that's still crafting its next chapter. As we reach the end of our cosmic journey through the birth of galaxies and planets, let's pause to marvel at a simple, profound truth the universe is still creating. Picture the cosmos as a living tapestry, its threads of gas, dust, and light forever weaving new galaxies, new stars, new worlds. From the fiery spark of the Big Bang to the gentle spin of protoplanetary disks, The story of creation is not a tale of the past, but an ongoing symphony played across billions of years. Galaxies merge, stars ignite, and planets form in distant corners of the sky, each moment a new verse in the universe's endless song. This is the story of a universe still being born, a reflection on its ceaseless creativity, and a quiet invitation to rest in its wonder as you drift towards sleep. Let's imagine the cosmos today, 13.8 billion years after its birth, alive with activity. In the Orion Nebula, just a short cosmic hop from Earth, molecular clouds glow with the light of newborn stars, their protoplanetary disks spinning, crafting planets as we speak. Across the universe, galaxies collide, their gas-sparking waves of star formation, like ripples spreading across a starry pond. In distant clusters, the cosmic web still gathers, matter-forming galaxies that will shine for billions of years to come. It's as if the universe is a tireless artist, never content to stop, always adding new strokes to its canvas of light and matter. This ongoing creation is driven by the same forces we've explored: gravity's gentle pull, the fusion in stellar cores, the collisions in protoplanetary disks. In galaxies like our Milky Way, stars are born every year, their deaths as supernovae scattering elements that will form new worlds. The Andromeda Galaxy, our nearest neighbour, is hurtling toward us, set to merge in a few billion years, creating a new galaxy filled with fresh stars and planets. Even black holes, those silent giants at galaxy centres, play a role, their gravity-stirring gas to fuel star formation like a cosmic conductor guiding the orchestra. The planets forming today are as diverse as those in our solar system. Some are rocky worlds like Earth, cradling the potential for oceans and life. Others are gas giants like Jupiter, or strange exoplanets, super-Earths, mini-Neptunes, or worlds orbiting twin suns like something from a dreamer's tale. Astronomers using telescopes like the James Webb Space Telescope glimpse these forming worlds, their disks glowing in infrared, revealing the universe's creativity in real time. It's like watching a cosmic nursery where new planets are born, each one a unique creation, shaped by the same processes that built our home. This endless cycle of creation connects us to the cosmos in a profound way. The atoms in your body, carbon, oxygen, iron, were forged in stars that died long ago, their materials recycled into the Earth you walk on. The Milky Way, our galactic home, is still forming stars, still shaping its spiral arms, still part of the universe's ongoing work. You're a living piece of this cycle, a spark of stardust carried through billions of years, dreaming now under a sky that's still crafting its next chapter. It's a humbling thought, isn't it? That you're part of a universe that never stops creating, always spinning new stories in the dark. This story also reminds us of the universe's patience. Galaxies take billions of years to form planets, millions to coalesce, yet the cosmos never hurries. It builds slowly, deliberately, like a gardener tending to a vast field, knowing each seed will bloom in its time. This patience is a quiet comfort, a reminder that creation is a process, not a moment, and that every ending, every supernova, every galactic merger is a new beginning. It's a cycle that feels almost alive, as if the universe is breathing, dreaming, and creating with every turn of its cosmic wheel. As we reflect on this journey, we've wandered from the Big Bang's first spark to the swirling disks where planets form, from the chaotic youth of galaxies to the quiet spin of Earth. We've seen how gravity weaves clouds into stars, how stars forge elements, and how dust becomes worlds. We've peered through ancient myths and modern telescopes, finding wonder in the cosmos's endless creativity. Each step has brought us closer to the universe's heart, a place of constant renewal where galaxies and planets are born, die, and are born again. So where are you tonight, and what time is it in your corner of the cosmos? Are you curled up under warm blankets with the stars outside your window, or resting quietly in a far-off place, the night sky a distant glow? If this cosmic tale has soothed your mind or sparked a quiet wonder, I'd be ever so grateful if you gave it a like, maybe tapped subscribe, and shared this gentle journey with others. It helps our little community of dreamers grow, bringing more souls to this tranquil corner of the universe where curiosity meets rest. As we close this story, let's hold on to the image of a universe still being born, its galaxies spinning its planets, forming its stars, shining in the dark. You're part of this creation, a fragment of stardust shaped by the cosmos's endless work, dreaming under a sky that's always crafting something new. The universe is still weaving its tapestry, still singing its lullaby, still inviting you to rest in its wonder. Sleep well, dear traveller, and may your dreams drift among the stars, carried by the gentle rhythm of a cosmos forever in bloom.